Today on How It's Made. American footballs. We touch down at the factory to see how they're made. Electric guitar amplifiers, giving rockers a needed boost. Marbles. Ever lose yours trying to figure out how they get those coloured swirls inside? And aeroplane propellers. Time flies on this production line. But first... In 1869, players in the first American football game used a round ball like in soccer. It was tough to carry and awkward to throw. The current shape enables a better grip and passing on an arc that's unique to football. Odd-shaped balls, but with good reason. A lot of people handle an American football before it ever gets to the field. These balls are traditionally made from cowhide because it wears well over time. The 4 sections that make up the ball's skin are cut out using a die. A stamping machine then brands the skin with the company logo. Other markings are placed elsewhere on the ball, depending on the design of the model being made. Each of the sections goes into a machine that trims the piece's combined weight down to spec. To strengthen the skin, cotton and vinyl linings are sewn onto all 4 sections. Then they are placed in a die that positions them to receive another set of markings. These 4 white lines will form 2 stripes when the sections come together. This is purely aesthetic and varies according to the football model. Now it's time to sew the top sections together, and then the bottom ones to each other. Exactly how many stitches this takes is the company's closely guarded secret. This press makes a hole in one of the top sections for the air valve. 8 holes are made in the top sections for laces that will hold the skin tightly around an inflated bag called a bladder. To join the ball's top and bottom sections, a seamstress first cups them and then joins the edges together. She sews the leather inside out to make the stitches less visible. Later, by reaching through the opening between the lace holes, workers will turn the skin right side out. This is also where they'll insert the bladder. It's important to flatten the 4 seams. To do this, each one is placed on a wheel as a roller passes over the top. This keeps the ball from being bumpy when the skin is stretched over the bladder. A 15-second steam softens the leather and makes it easier to manipulate. A concave press flattens the seams at the tips. This will also keep the ball smooth when it's inflated. Time to turn the skin right side out. It's placed on a metal bar before being turned from inside out to right side out. A bar is run along the inside to reshape the skin. The bladder is made of polyurethane, a type of plastic, with a vinyl patch reinforcing the lacing area. After the bladder is squeezed inside the skin, the end of the air valve is snipped off to keep it out of the way. Then the bladder is inflated a little to make it rigid enough for lacing. The ball is steadied using clamps before an awl is used to thread the lace through the holes. Just 1 vinyl lace is used, measuring 1.2 meters. It worms through both sides and then down the center and through all the holes once again. The lacing is spaced a little more than 1 centimeter apart, wide enough to comfortably grip for that magic pass you've got in mind. Next, the balls are temporarily overinflated. Steel molds surround them to ensure they assume the correct shape. After 90 seconds, the extra air seeps out. Finally, the balls are inspected to ensure they're up to standard. Fully inflated, a ball must weigh no more than 425 grams. It should measure 55 centimeters through the middle and 71 centimeters around both ends. After some teamwork in the factory, these balls are ready for kick-off. A guitar amplifier is a boxed unit containing an amp to boost the electronic signal and a loudspeaker. Some amplifiers use state-of-the-art silicon chip circuitry, while others use traditional vacuum tubes. If you want to give up playing air guitar and annoy the neighbours, a good amplifier is a sound investment. The amp's electronics are housed inside a metal chassis. This model's chassis is made from a sheet of steel that's less than 1 millimeter thick. A computer-guided machine, called a turret punch, cuts the contour and pierces a series of holes and slots for the controls. Then a computer-guided bender is used to shape the chassis' cutout. Elsewhere in the factory, the amp circuit board takes shape. It'll go inside the chassis. A drill makes tiny holes in a laminate board that's coated with copper. The holes are for the board's various electronic components. An automated silkscreen printer now applies a diagram of the electrical circuitry in ammonia-resistant ink. Then the board goes into a machine called an etcher, which uses ammonia to dissolve the copper coating. Copper shielded by the ink diagram stays intact. The machine then rinses the board with sodium hydroxide to dissolve the ink, leaving behind just the circuitry diagram in copper. This copper configuration will conduct electricity to the circuit board components. Automated machines insert the smaller components. Here's what that looks like in slow motion and at actual speed. A machine folds over the leads of some larger components to secure them to the board until they're soldered. Then, large irregular parts are installed by hand. Among them, the sockets that hold the tubes which power the amp. The ribbon connectors that join different areas of the circuit board. And the wires that connect external components to the board. Everything is permanently fixed in place in one shot using a process called wave soldering. The circuit board runs through a bath of molten tin and lead. In just a couple of seconds, the liquefied metal hardens, bonding the components securely. Back to that steel chassis we saw them bend into shape earlier. Since then, it's been painted black. The control markings, logos, and other information are applied using a silkscreen printer. The final assembly begins. First, the circuit board is screwed into the chassis. Then the preamp tube is plugged into the appropriate socket on the board. This tube boosts the electrical signal coming from the guitar and feeds it to the output tubes, which up the voltage level, making the signal stronger and louder. After control knobs are installed and the bottom of the chassis is covered, the output tubes are inserted and clamped, the number of which varies according to how many watts of power the amp is designed to produce. The chassis housing the electronics goes into a box. This factory builds its boxes from high-grade Baltic birch plywood. Other companies often use domestic plywood, MDF, or even plastic. After covering the box in leatherette and adding corner reinforcements, the two remaining components are installed. The spring reverb, and the speaker. As the guitar's electrical signal runs through the amp, part of the electrical signal diverts to one end of the spring, vibrating it. The spring's other end picks up this vibration and sends it back through the amp as a delayed signal. That reverberation combines with the original signal to produce a bigger sound. Rock on! Coming up on How It's Made, marbles, because you're never too old for playground games. And aeroplane propellers, this one will have you in a spin. See you after the break. The ancient Egyptians and Romans played games using small balls of stone, clay or marble. Today's marbles are made of glass and used for industrial tasks as well as games. Glass is inexpensive and durable, and some of these swirly designs can really get you noticed in the playground. To make marbles, this company melts recycled glass along with marbles made earlier but rejected for being the wrong size. All this goes into a kiln heated to 1,204 degrees Celsius. After 16 hours, a door at the bottom of the kiln is opened and the molten glass flows out. A shearing device cuts the stream every half a second, forming segments called slugs that become marbles. To make different sized marbles, the device is adjusted to cut at shorter or longer intervals. The slugs slide down chutes, landing between grooves on spinning cast iron rolls. The spinning keeps the slugs from sticking. They'll need 72 hours to cool completely, but their final appearance is already set. That was determined back in the kiln when the airflow drove the heat to melt the glass and mix the colours. These channels separate the good from the bad. Openings along the way weed out the ones that are too big or too small, and collect the ones that are just the right size. More intricate marbles are made by hand. This craftsman first preheats some clear glass in a small oven. Then he breaks off a piece of coloured glass. After the clear glass has melted in the furnace overnight, he gathers some on a steel rod. Then he picks up a chunk of preheated coloured glass with it. He forms a knob and works the mass into a long string that's up to 5 meters long and as thin as a noodle. He'll use various colours to decorate the clear glass cores of the marbles. A clump of melted clear glass gathers on the rod, and it's shaped over wet newspaper, which won't stick to hot glass. After the end is shaped, the clump is then rolled over several preheated coloured glass strings. Then it's back to the furnace. These steps are repeated up to 3 times, and the clumps are rolled on a metal table to even out the surface between each trip to the furnace. Then a layer of clear glass is added on top. Now the clump is stretched to about ½ a metre long using another tool. This will be used to make several cores. To make the second layer of the core, a 5 centimetre long segment is rolled onto coloured glass slivers called ribbons. After they've been rolled in the furnace and melted, the ribbons are flattened with pliers and the excess is snipped off from the ends. The core and the ribbons are wrapped in a layer of clear glass, which is then shaped by hand. The core is rolled on more glass strings. Then it's back to the furnace to melt them. One more clear glass layer is added and the inside is finished. The craftsman shapes the glass with several metal and wooden tools. He measures the diameter with metal calipers and gradually sculpts a sphere. He'll make up to 5 marbles from this segment, ranging up to the size of a golf ball. After scoring the glass with a knife, he places it in the open end of a pipe to hold it. Then he gently taps the rod, which breaks the glass and releases the sphere. He melts away the bump left at the spot where the glass broke. Next, the marble goes into an oven at 530 degrees Celsius. The oven slowly cools overnight to strengthen the glass. Eye-catching and clearly a cut above, marbles are great. Just be sure not to lose them. An aeroplane propeller usually has 2, 3 or 4 blades, the angles of which can be adjusted by the pilot in response to airspeed and flight conditions. A propeller's main parts are made of aluminium because it's critical to keep it as lightweight as possible. The next item is sure to have you in a spin. The propeller's blades attach to a hub. This piece of aluminium is on its way to becoming that hub. Like the starting pieces for all parts, it was forged beforehand into a rough version of the final shape. This sophisticated computer-guided mill now machines the piece. 40 minutes later, the hub is finished and ready for assembly to the engine. This roughly shaped piece is about to become one of the propeller's blades. A lathe machines it to the final shape. Liquid lubricant washes away the metal shavings and cools the friction-generated heat. The lathe first forms the shank, the end of the blade that fits into the hub. The next milling machine cuts the blade's shape. Now the finishing steps, done manually because they require a keen eye. Using first a rotary sander and then a belt sander, the marks the machining process left behind are ground away. The metal is buffed with a polishing wheel. Then the blades are dipped in a strong detergent. This acidic solution eats away any dirt, oil or grease on the surface of the metal. After that, the blades are put in a bath of water and chromic acid. This seals the pores in the metal, fending off corrosion. The factory tests all critical parts for surface defects by dipping them in a fluorescent solution that leaches into any imperfections. After rinsing, the parts are inspected under black light. A blue glow means they're okay. Any imperfections show up as bright fluorescent green. The defective part is either repaired or rejected from the production line. Blades that get the blue light move on to the paint shop. A coat of black on the backside prevents sun reflecting into the pilot's eyes. And for safety reasons, stripes are added to make the spinning blades visible. Next comes a de-icing boot, a rubber-encased electric heating element that prevents ice buildup. The rubber is highly durable yet flexible enough to mold to the curve of the blade. Next, a part of the blade shank is lubricated with grease. Then a strong steel ball bearing system is installed. This will hold the blade securely in the hub whilst enabling it to pivot to change its angle. The shanks of the 3 blades fit right into this steel part called the fork. It keeps all the blades at the same angle. Next comes the pitch change rod. The term pitch refers to the angle of the blades. Engine oil will exert hydraulic pressure on a piston that moves the pitch rod, which advances the fork, rotating the blades to the required angle. The pitch change rod is temporarily removed and sealant is applied to the top half of the hub. It's then placed over the bottom half that contains the ball bearing set. A rubber seal is added, then a sturdy spring to provide the required counter pressure. The piston and pitch change rod, which are now attached to each other, are threaded onto the fork. Another seal is added. This one prevents leaks from the top of this cylinder that will contain the engine oil. A special tool is used to tightly torque the cylinder down against the hub. Assembly is now complete, and the propeller is ready to go for a spin. Chocks away. So, whether you're looking to score with your odd-shaped balls, or trying to impress with a wailing guitar solo, or perhaps simply reliving your playground days, now you know how it's made. Today on How It's Made. Engine blocks. We take a trip to the hood. Gobstoppers. Workers at this factory take their sweet time. Drum shells. We'll round out all the details on how they make them. And drums. This one will take some beating. But first, the engine block is the largest single piece of metal in a car. It houses and links all the engine's components, such as the cylinders and pistons, and it contains passages for circulating coolant. The engine block is where combustion converts into mechanical energy that drives the transmission, propelling the car. Engine blocks used to be made of iron. Today they are mostly made of lightweight aluminium alloy for fuel efficiency. An engine block is a one-piece component cast from a sand mould. To make the mould, the factory mixes glue and a hardener with zircon sand. This combination of materials can withstand the intense heat of molten metal, but only for one casing. Each mould is made up of sections called cores that fit together. To make each core, a machine blows the sand and glue mixture into a master mould made of iron. It injects a gas that activates the hardener, which solidifies the mixture. This is the base core to which the other cores will attach. The base core travels down an assembly line to receive the other cores. The next core moulds the engine block's cylinder bores, which will house the motor's pistons. A robot inserts iron liners into 6 holes in the core. They prevent the aluminium walls of the bores from wearing out from abrasion. The base core receives 17 other cores. The ones for engine block areas through which oil will flow are coated with talcum powder. This keeps sand particles from sticking to the aluminium and getting into the oil. The machines glue certain cores, so they'll stay intact when the robot flips them upside down and become attached to the rest. These are the last two cores. The mould is now fully assembled and ready for casting. Aluminium ingots are loaded into a device called an elevator bucket. It positions them above the jet melter, a gas-fired furnace. The bucket drops the ingots into the 800 degrees Celsius fire, liquefying the aluminium. Just before casting, the cylinder bore liners are heated using a high-frequency electric current. Aluminium will bond better to hot metal. The moulds are filled from the bottom to avoid contaminating the metal with aluminium oxide. Oxide forms when molten aluminium comes into contact with the air. Pouring into the top of the mould would expose the metal to oxygen, and the pouring action itself would mix in the oxide. After the casting, the mould spends 6 hours in a thermal sand reclaim oven that breaks down the glue so the sand falls away. The heat also strengthens the metal. The cast aluminium engine blocks emerge, needing just some minor finishing. Robots turn them upside down to spill out any loose sand. Machines saw off the risers, extra metal that fed the mould cavity to compensate for the 7% shrinkage that occurs when liquid aluminium solidifies. Finally, computer-guided tooling equipment performs a rough machining of the metal. This brings the engine block to a near-finished state. The engine plant that buys them does the final machining before installing the engine parts. Every engine block this factory produces passes through an automated vision system that inspects the engine, so you shouldn't be breaking down anytime soon. Jawbreakers, also known as gobstoppers, have been enjoyed by the sweet-toothed among us for decades. You pop one in and slowly suck or chew through up to 10 layers of colours and flavours. Sometimes there's bubble gum in the middle for an even longer lasting finish. The large ones are just for show. Most gobstoppers are smaller than a golf ball. To make their bubblegum centres, synthetic rubber is blended with powdered resin which will dissolve the rubber. A thickener, a preservative, and an oil called soya palm stearine are added, so the sweet won't stick to your teeth. After mixing and steaming at 148 degrees Celsius for 4 hours, the batter pours into trays to cool. Sugar, colouring and flavouring would deteriorate in the heat, so these are added later. There's enough of this base to make gum centres for 450,000 gobstoppers. After 24 hours, the batter's hard. It's chopped up and blended with corn syrup to make it softer and sweeter. "45 kilos of finished gum is added. Now natural and artificial flavours are added, which can include lemon, orange, strawberry, grape and tutti frutti. Then icing sugar is added. It makes the gum smoother to chew than regular sugar would. The batch is dumped into an extruder that shapes 2 continuous streams of batter known as rope. Another extruder divides each rope into 6 hollow tubes. The cavity inside will become pockets of air inside the gum centres. The next machine slices the tubes into 1 metre long segments. A mechanical arm pushes the segments into the channel of a forming machine. Steel rolls then slice through the tubes and shape them into balls. The balls range in diameter depending on the size of the gobstoppers being produced. Air blows through perforations in a cooling tunnel to cool and firm the centres. Then they fall onto another forming machine which restores their round shape. Other gobstoppers have hard centres. The machine that makes them feeds powder into dies, then applies up to 5 tons of force to compress the powder into a solid sweet. Now for the rest of the gobstopper. First, the sweet centres are dumped into what's called a coating pan. A hot mixture of water, corn syrup and food colouring is added. Then they add dextrose, a type of powdered sugar. The pan rotates for 20 minutes as warm air dries the ingredients over the centres. The factory repeats this step 10 times for each layer. Making a gobstopper takes 4 days. This batch gets special treatment. These gobstoppers are speckled with different colours, giving them what this company calls the psychedelic look. After the sweets have dried for 24 hours, pinches of powdered carnauba wax are added. This gives the gobstoppers a shiny finish. Sliced open, you can see these gobstoppers have 10 layers of flavours and sugar surrounding either solid sweet or bubble gum cores. They measure 5.7 centimetres in diameter, and a gobstopper is 90% sugar. So if you're counting calories, keep your gob short. Coming up on How It's Made. It's a 2-part special as we look at how they get around to making drum shells. And while we're on a roll, we'll tell you how drums are created. See you after the break. Almost every culture has marched to the beat of its own drum. Drums have been part of different civilizations for thousands of years. The earliest drum shells were hollowed out logs or gourds. Different sizes created different sounds. Today, drum shells are more sophisticated, but the beat goes on. To make drum shells, an enormous rock maple log is sliced into several boards. Maple is ideal for making drum shells because its hardness allows sound to resonate fully. Each of these maple boards will be transformed into one drum shell. The boards are fed to a rip saw, which cuts them to the correct width. This varies depending on the size of drum being made. Then each board goes into a planer, which shaves it thinner. The board is aligned with markings on a saw table. This positions the board to be cut to the correct length. A radial arm saw does the job neatly. Now, each board is sized up in preparation for tapering. They're placed at an angle in a jig. Then the end is moved against a router to taper it. It takes a few passes to get it just right. The taper needs to be about 15 centimetres long. The other end of the board is thinned to the same dimension. These tapered ends will make it easier to bend the wood into a drum shape later. They also act as scarf joints, which will fasten the ends of the boards together when it's bent round. The board needs to be softened, so it's placed in a steam box for about an hour. It's now pliable enough to wind around a hot cylindrical form. Steel banding secures the board to the bending form, where it will spend 10 to 15 minutes. The ends are prized apart, and glue is applied between the tapered tips. Then the shim that was holding the ends apart is removed so they stick together. A wooden guard is placed over the glued joint. This nylon mesh band is a clamp. It's wrapped around the drum shell, and a screw is turned to pull the band tightly around the wood until it reaches 35.5 centimeters in diameter. Then, more than a dozen steel clamps are fastened onto the joint. All these clamps will prevent any gaps from occurring in the joint as the glue sets overnight. With the joint sealed, the drum shell now spins while a cutter shaves down the edges to make it a true round shell. Another cutter bores into the shell, making a smooth edge and rounding the inside. The drum shell is turned around so it can be cut from another angle. As the shell spins, a high-speed cutter shaves the outside from top to bottom. This makes the surface very smooth. It takes about a week to make a drum shell from solid wood. And it will be able to stand up to a real beating. We've shown you how a drum shell can be created from a maple plank. But a newer technique involves layering multiple plies of wood. This process is called laminating, and you can hear the difference. There's more than one way to beat a drum, and there's more than one way to make one. The laminated drum is an instrument of change. Its sound is crisper than a drum crafted from a single piece of wood. To make one, 11 sheets of maple are layered together. Here, the last one is being attached using a special adhesive. This outer layer is made from luxurious bird's eye maple. Rollers press all the layers together to ensure they stick without any gaps. A cut is made through the overlap to create a perfect seam. A robotic drill takes over. It drills holes of various diameters. The small ones will hold hardware. This larger one is an air vent. A computerized router then cuts the bearing edges to a 45-degree angle. And it's sanded smooth. All the edges are checked to see that they're level. If they're not, the drum heads won't fit properly. An adhesive is applied to the air hole and a plastic vent is inserted. Next, brackets called lugs are inserted into the other holes and screwed in. There are 10 lugs spaced 36 degrees apart. They hold the rods that will attach the heads to the drum shell and also enable the drummer to adjust the tension on the heads. A lever is attached to control wires called snares that will be strung across the bottom head. It's called a snare strainer. Then a plastic drum head is fitted over the bottom of the shell. The counter hoop goes on next. It has small tabs which are aligned with each lug. Tension rods are slid into the holes in the tabs. Using a drum key, the head is tightened to an even tension across the shell. Now it's blasted with a heat gun to shrink the plastic and remove any wrinkles. Another plastic head is placed on the top bearing edge. Since this head is the one that gets played, it's twice as thick as the bottom one. The chrome rim is placed on it and the tension rods are tightened. These brass brackets will hold the snare wires. They're slid under the snares that are stretched tightly across a jig, putting one at each end. The length is measured, then the snare wires are soldered to the brackets. The wire is snipped on both ends, and each wire is unlocked from the holding device. When the snares are removed, they're held together by the brackets. A nylon strap is slid into one of the brackets. Then the strap is attached to a fixture just above the bottom head. The other end of the snare is attached to the strainer, the lever that will apply tension and release it, controlling its distinctive buzz. For a bigger sound, there's the bass drum. It's made with wooden hoops. The hoops are attached to the drum shell with steel claws. As the claws are screwed to the hoop, the drum head is pulled just tightly enough to produce that low-pitch bass drum sound. A sound production indeed. So, whether you've got your head under the car bonnet trying to make sense of it all, or your mouth is full of gob-stopping, jaw-breaking sugar, or perhaps you think of yourself as the next Keith Moon, now you know how it's made. Today on How It's Made. Lighters. It must have been a bright spark who invented this one. Dinosaur models. The skeletons will come out of the closet for this report. Hockey pucks. We visit a factory whose goal is always net profit. And high-pressure cylinders. The operative word is containment. But first, it's a case for combustion. Spin the wheel and you have an instant flame. Flip the lid and the flame is extinguished. A version of the lighter first appeared in the 19th century. At the time, it was more of a conversation piece than anything else, a curiosity that ignited plenty of interest. Lighters aren't a novelty anymore, but they're still a hot commodity. To make lighter cases, a machine uncoils brass from a spool, pulling it to a press. The press stamps the brass repeatedly to shape both the top and bottom parts of the case. They're collected and placed on a revolving table. Then they're slid onto a hinge to link the top and bottom pieces. An electrode welds the hinge to the case, and then a mechanical arm knocks them down a chute to a worker who inspects the welding job. As the cases move on a conveyor system, they get a quick buff to prepare them for plating. The lighter cases are now plunged into a series of washing solutions and rinses, followed by a nickel solution, then a chrome one. It's the finishing touch for the lighter cases. It's time to move on to the inner workings. A die shapes a piece of steel to make the inside cases. Mechanized arms then place a tube and plate in the case. The tube will hold the flintstone, and the plate will form the top of the inner case. Epoxy seals them in place, and the cases move through a curing oven to harden the epoxy. A pile of flint wheels are arranged so that the teeth are in the proper direction. Grippers load the flint wheels into an assembly jig. These cams will eventually act as a catch for the lighter lid. A gripper places the cam in the jig beside the flint wheel. The assembly jig now receives little brass eyelets between the flint wheel and the cam. The machine slides the inner case over the flint wheel, cam and eyelet. And an automated device rivets it all together. A machine lowers a wick to the eyelet and threads it through. Blades move in from the side and snip the wick. This machine stuffs pieces of cotton into the inner case. The cotton will soak up and retain fuel when the consumer adds it later. Steel plungers tamp down the wick and cotton. Here, a die punch cuts a piece of felt to size. Automated arms pick up the felt and shove it to the top of the inner case. Grippers place a flint spring in the case just over the flint stone. Pneumatic screwdrivers drive the screw home. A rubber wheel spins the flint and sparks fly, as a light sensor checks their intensity. After the flint check, technicians install the inner unit in the case. They check the fit. They test the function. This looks like it's an open and shut case. It takes a lot of backbone to make one of these. Real dinosaur bones, millions of years old, are used to make life-size replicas. You'll find them on display in museums. They're very exact. Dead ringers for the real thing. The dinosaur looms large once again, brought back to life thanks to an evolution in casting techniques. Building these replicas is a job that can involve both high-tech know-how and hands-on skill. They start with the real thing, an ancient find. This is a dinosaur's upper jawbone. It's laser scanned, producing a three-dimensional image. The scanner feeds the image to a computer. Then it's time to go to print. But this isn't an ink and paper job. This tray is filled with plaster powder. The printer outlines the jawbone shape with a liquid hardener. The result is this plaster cast of the jawbone. There is a more traditional way to make one of these replicas. Plywood is arranged around this dinosaur bone. Then sheets of clay are layered on the wood and pressed to the bone. With a clay pick, a 90-degree angle is made at the bone to give it a clean line. Using more clay, a spout and riser are built at one end of the bone. An ID number is etched into the clay. Then, liquid rubber is painted onto the bone and the abutting clay. Fiberglass sheets are placed on the rubber, which is wetted with a polyester mix. They work the fiberglass into the shape of the bone. A red gel coat is painted onto it. It's a color code to identify the species, a duck-billed dinosaur called Lambiosaurus. One side of a mold has now been created. When both sides of the mold are fabricated, they're paired up. And this mold is complete. The rubber layer inside picks up the bone's detail, while the outer fiberglass one will hold the rubber rigid as a polyester and water mix is poured into the spout. It takes about 45 minutes to harden. Now it's time for the big reveal. An exact replica. Next, part of the skull is formed. This part is made with hollow fiberglass instead of solid polyester. This will ease the load on the steel framework later. All the larger bones are cast with hollow fiberglass because of weight issues. This is a mastodon head. Up to 300 pieces are molded to produce these skeletal replicas. On one side of the skeleton, scales are sculpted onto a clay-like fill to demonstrate how a dinosaur would look with skin. The other side remains just the bare bones, to give the viewer an inside look. A little glue completes this spine work. Then the skull is mounted. When the front leg goes on, this dinosaur is ready to go. It's a real museum piece. Coming up on How It's Made, hockey pucks. They need to be tough because they take a real beating. and high-pressure cylinders, containers that work well under pressure. See you after the break. Early hockey pucks were made of wood, but for informal games, a stone or a piece of frozen animal dung would suffice. Eventually, rubber became the material of choice. The modern puck is 7.5 centimetres in diameter and 2.5 centimetres deep. Smashing. 11 different ingredients go into making these hockey pucks. The recipe begins with natural rubber. 2 types of oil make the rubber durable. Certain minerals act as curing and anti-aging agents. And a form of coal dust called carbon black serves as a filler. The ingredients are fed into a preliminary mixer. First, the slabs of natural rubber. Then antioxidants to lengthen the rubber's lifespan. Then one type of oil to help blend in the dry chemicals. Then another type to refine the rubber's rigidity level. Then additives such as calcium carbonate and sulfur to help cure the rubber during the moulding process. And finally, the carbon black filler. After 10 to 15 minutes of this preliminary blending, the mixture goes down a chute and onto a conveyor belt, which transports it to a machine called the mill mixer, which will perform the final mix. At this point, more natural rubber is added. Then another harder rubber that will make the hockey pucks more resilient is added. The recipe is formulated to produce a very tough rubber, one that can stand up to the rigours of repeated blows from a hockey stick. It's critical that the ingredients blend evenly. That's why the rubber is continuously cut while it's mixing. In the company lab, technicians evaluate a sample from each batch. This device is called a rheometer. It analyses what's called the curing curve, how the rubber hardens and to what degree. A computer compares the curing curve to the quality model. If they match, the batch gets the go-ahead. The rubber hasn't yet gone through the curing process, so it's still malleable. An extruder squeezes it through a round die. This produces logs about 1 metre long and 7.5 centimetres wide, the exact diameter of the hockey puck. The next machine slices each log into 39 pieces. Each piece is 2.8 centimetres thick. These pieces are called preforms because at this stage they're not quite fully formed pucks. Workers put them into compression moulds. Each mould cavity is the exact size of the finished hockey puck. Cover goes on. Then the moulds go into a curing press, which compresses the preforms and heats them to 149 degrees Celsius. It takes about 18 minutes for the rubber to cure. The preforms come out as hockey pucks, rock hard and 3 millimeters thinner than before. They cool for 24 hours. During the compression phase, excess rubber oozed out and stuck to the pucks, so each and every puck is run manually through a trimming machine. There's excess rubber stuck to the moulds as well. The factory scrapes it off, grinds it up, and uses it as a filler in subsequent batches. The mould embedded a dimple pattern on the puck's edge. This texture creates friction between the puck and the hockey stick. The more friction, the better stick control, and the greater the hockey puck's net worth. High-pressure cylinders are metal containers designed for storing gases and for dispensing them at high pressure. Think fire extinguishers and oxygen tanks. The contents are often flammable, so the challenge is how to make these often life-saving cylinders safe yet still easy enough to use. These cylinders are made of a steel alloy containing chromium and molybdenum. Their manufacture begins with discs that have already been heat-treated at 730 degrees Celsius for 36 hours. Now they go into the first of 5 hot chemical baths that will help the metal flex. After a quick drying period, each disc moves over a die. This process is known as deep drawing, because a series of machines will gradually draw out the disc to the shape of a cylinder. A mandrel press begins stretching the metal, applying up to 800 tons of force, the weight of 2 fully loaded jumbo jets. Shaping the cylinder from just one piece of metal means it will be seamless, and that is a key safety feature. After the disc comes through, steel jaws clamp down on the mandrel and the cylinder slips off. Now another press stretches it even more. This machine applies 250 tons of force to continue forming the walls of the cylinder. That liquid is a coolant to prevent overheating. The cylinder goes through as many as 3 presses, each one stretching it another 60%. This press forms the closed bottom end into a concave shape that reinforces the base. A bandsaw now slices up to 10 centimeters off the other end, which will become the top of the cylinder. Next, a torch heats that end to 982 degrees Celsius for 90 seconds. In a process called hot spinning, a cylinder is placed in a device that spins at 1000 RPM. As a torch maintains the temperature, the machine shapes the edges of the searing hot metal into a curve. In this way, the machine gradually closes off the top end and shapes 2 rounded areas called the shoulder and neck. Making these areas curved is the best way to contain pressurized gases. Curves spread out the stress on the metal. A sharp corner would focus the stress in one spot. The only exit for gases will be through a valve at the top. "18 cylinders are placed in a furnace heated to 900 degrees Celsius. After 90 minutes, a machine then dunks them in a chemical bath to cool for 6 minutes. The cylinders are then reheated to 650 degrees Celsius for 90 minutes, then left to cool for 2 hours. These transitions between hot and cold, a process called tempering, strengthen the metal and make it somewhat flexible. Now, a cutting tool carves open the neck and cuts the threads inside it. This provides the best seal when the valve screws into the neck. Workers clean the cylinder's surface using a process called shot blasting. A machine shoots these tiny steel pellets at the cylinders at very high speed. To be tested, the cylinder is filled with water, then it's sealed off and immersed in water. The machine then adds more water to the cylinder and gauges how well it withstands the extra pressure. The inside is rinsed with hot water, then dried and cleaned with purified air. Next, a hydraulic press indents the shoulder of the cylinder with legally required markings, such as the manufacturing date and the serial number. A machine then stretches a steel collar over the neck. Another device, called a valver, tightly screws on the valve, creating a leak-proof seal. After a trip to the paint shop, these cylinders are ready to be filled and perform under pressure. So, whether lighters bring warmth and light to your world, or realistic dinosaur models have you a touch scared, or perhaps you're amazed at what goes into the making of a simple hockey puck, now you know how it's made. Today on How It's Made. Balloons. We'll do some rubbernecking at the factory. Wallpaper. We're on the paper trail to tell you how they make it. Frozen French fries. A food factory where everyone chips in. And incandescent light bulbs. We shed some light on how they're produced. But first, the sight of a balloon floating in the air sends a message that you're special. But balloons weren't always so delightful. In earlier days they were made of dried animal bladders, a bit of an unpleasant concept. In the 19th century, someone invented a rubber balloon, and that trial balloon took off. Balloons were first mass-produced in the 1930s, and after that, the sky was the limit. To make balloons, dye is poured into a tank of latex. It's filtered through cheesecloth to remove any lumps. Agitators at the bottom of the tank mix it up for 15 hours. This distributes the colour, and it also keeps the latex active so it doesn't congeal. These balloons come in 53 different shades. Nozzles spray hot water onto balloon forms to clean them as they move onto a system of rollers. A fixture then flips and dips the forms into a tank of coagulant that carries an electrochemical charge, which will attract the coloured latex. On this fixture are balloon forms freshly dipped in blue latex, while below, a tank full of latex rises, coating more forms on the underside. Once this job is done, the fixture flips back, moving the balloon forms to an upright position. While below, another tray of balloon forms takes the plunge. The latex dries quickly as a conveyor moves the balloon forms forward towards spiralling brushes. The brushes roll up the bottoms of the balloons, creating lips. The lips will make it possible for people to grip the balloons in order to inflate them. The fixture flips again, and the balloons nosedive into a hot water bath. They soak for up to 16 minutes. This step is critical. It leaches out all the impurities, including a protein that causes latex allergies. The hot bath also triggers vulcanization or rubberizes the latex. The balloons travel to another station. Here the fixture dips them into a mix of talcum powder and water. This will allow them to be more easily stripped off the form. Now it's time for the forms to shed their latex skins. As the forms pass through this station, air jets inflate the balloons. Rollers at the top grab the balloons as they fill with air and pull them away from the forms. The rollers shoot the balloons upwards and they topple onto a conveyor belt. Next, the balloons are piled into an industrial washing machine and a cleaning solution is added. The machine heats to a steamy 71 degrees Celsius, while the balloons tumble and nozzles spray water onto it. This doesn't just clean the balloons, it completes the vulcanization of the latex. Now it's time to see if they can stand the test of inflation. A machine blows air into a huge heart-shaped balloon, and the heart swells, but doesn't break. It's checked for imperfections like blisters. Now it's time to stretch your imagination by making interesting shapes with the finished product. The use of wallpaper dates back to 15th century England. At first it was seen as a cheap substitute for tapestry and panels. But over time, wallpaper gained a wider appeal. Even today, people are still stuck on the look. When it comes to variety in design, wallpaper has really got it covered. To make the vinyl base for wallpaper, water is poured into a giant mixing bowl with stabilizing powder and a lot of plastic pellets. Solvent is added, which helps to dissolve the plastic pellets into the mix. Large beaters stir it all up. And just as if the factory were making pancake batter, they add ingredients incrementally. A little more powder to thicken the mix, and more plastic pellets for good measure. When the mix reaches the right consistency, it's poured between rollers onto one side of special paper. An applicator roller spreads the vinyl mix evenly onto the paper. A jumbo reel rolls it up and then unwinds it again. Here, nozzles fill trays with paste. Rollers pick it up and apply it to the back side of the paper. Electrically powered rollers pull the wallpaper through a gas oven, drying the paste. Then the paper is wound up again, creating a giant reel. A circular blade now slices through the centre of the paper. This turns the one roll into two, each of them 55 centimetres wide. A sample piece is pulled off and the paper is torn away from the vinyl. The vinyl is checked for smoothness and durability. Meanwhile, away from the production line, stylists experiment with paint. They brush colours on a design that they've selected. They select 5 to 6 different colour combinations because this design will be printed in many hues. Each colour requires a separate print roller. The design is engraved into each roller. Ink is applied onto one of the print rollers. As the wallpaper turns on a big drum, vinyl side up, the print roller transfers the image onto the paper. Each cylinder layers it in a different colour, building up the design. Darker colours are achieved by deeper engravings on the print cylinder because they transfer more ink onto the wallpaper. Conversely, shallower engravings produce lighter tones. When they have the final proof, they compare it to the original artwork. If the colours look right, the design goes into production. There's no turning back now. The ink is ready and the paper rolls travel through a web of print cylinders. Here, print cylinders build a dolphin design onto the vinyl side of the paper. To dry the ink, the paper travels through a hot blower system. This is the view from below. Photos are taken and viewed on a monitor to get a close look at the quality of the wallpaper print. If it passes inspection, they roll the wallpaper onto a big reel. Some wallpaper has a flat finish, but they often emboss it, making raised designs. This creates texture. Blades from above and below cut the wallpaper into 10-metre rolls. That's retail size. A conveyor system transports the wallpaper to a machine that shrink wraps it. And they're on their way to making a design statement. Coming up on How It's Made, frozen French fries, ready to travel from freezer to fryer. And light bulbs, an illuminating story. See you after the break. Most food historians believe French fries are actually a Belgian invention, originating in the 17th century, when poor people had to resort to frying potatoes instead of fish. During World War I, fries were popular with American soldiers stationed in Belgium's French-speaking areas, which may be how they came to be called French fries. This company makes its frozen fries from russet potatoes. Russets are oval, so they produce longer fries than a rounder shape variety would. Russets are also sufficiently crunchy when fried, and their lower than average sugar content means their flesh stays white longer. When the potatoes arrive at the factory, they travel along rollers that rub off any foreign matter, things such as soil, small rocks and plant parts. The rollers also scrape off the eyes. The potatoes then enter a washing station. As they spin in a revolving cage, water jets spray their surface, cleaning them thoroughly. Next stop, a sorting machine that divides the potatoes by size. It's made up of successive levels of vibrating grids. The shaking forces the smaller potatoes through the grid openings, separating them from the larger potatoes. The big potatoes become classic strip-shaped fries. The small ones become ring-shaped or cube-shaped fries. After sorting, the potatoes drop into a collection bin. Once full, its bottom hatch opens, releasing the potatoes into a giant steamer. After about 10 seconds in the pressurized steam, the skins are soft enough to come off with just a little pressure. That happens next in this machine, called the peeler. It looks like a giant clothes dryer, except that the drum is lined with brushes. As the drum tumbles, the bristles rub off the skins. As the skinless potatoes exit the peeler, workers inspect them, tossing any that have green or rotten parts, or pieces of skin still stuck to them. The type of fries in production determines which of two systems do the chopping: a series of rotary mechanical slicers, or a hydraulic system in which running water thrusts the potatoes against cutting blades. The freshly cut potato pieces drop into a canal. Flowing water transports them to a conveyor belt that will move them through the next phases. Now for a high-tech quality check. Each and every piece passes by a camera, in which a computer analyses size and colour. Any substandard chip is flagged and an air jet blows it off the production line. The good pieces fall into a water tank. As they soak, sugar leaches out of the flesh, so that they'll all turn out the same colour once they're cooked. Then, a process known as blanching. The pieces go into hot water, then cold water. This firms up the flesh and makes the potato flavour more pronounced. Then it's into the fryer. The potatoes cook for about 2 minutes in non-hydrogenated vegetable oil. As the French fries leave the fryer, excess oil drains down through holes in the conveyor belt to a collection pan below. The fries now pass through the freezer area, which is between -15 and -25 degrees Celsius. They take about 10 minutes to freeze. Once they do, an oscillating conveyor belt deposits them into chutes. Each chute has a built-in scale set to the package weight, which for this production run is 4 kilograms. Once that quantity accumulates, the bottom of the chute opens and the fries drop into a plastic bag. All the customer has to do is drop these frozen French fries into boiling oil for 2 or 3 minutes, and they're ready to serve. Don't forget your salt and vinegar. The incandescent light bulb is a rather simple device. Its base has 2 metal contacts which connect to a metal filament. The electric current's electrons collide with the atoms in the filament, making them vibrate. This energy heats the atoms to 2200 degrees Celsius, at which temperature they emit visible light. The light bulb factory has 2 production lines that eventually merge. One prepares the glass bulb. The other makes the mount, the electrical components that go inside it. At the start of the mount line, a machine cuts glass tubing into pieces of specific lengths. The cut tubes land on what's called a glazing wheel that runs them through a gas flame for about 7 seconds. This heats the glass enough to smooth the surface. The glazed tubes now enter a flare-making machine, which heats each tube until the glass is malleable, then stretches one end into a flared shape. The next machine loads 2 copper lead wires into the flare end. Then it inserts a thin glass cylinder called the exhaust tube. A trip through a series of progressively hotter flames softens the tubes. A press then moves in to squash them, encasing the wires in glass. At the same time, the machine makes a tiny hole in the glass in between the wires. This is to later remove the air from inside the bulb. It'll exit via the exhaust tube through this hole. Next, the machine separates the lead wires and forms the ends into hooks. These fasten to a filament, a thin wire coil made of tungsten, a type of metal that holds up well to heat. The machine coats the lead wires in a liquid form of another metal, zirconium. This lengthens their lifespan by making them more resistant to moisture inside the bulb. Like the tubes, the bulbs are made of an inexpensive type of glass called soda lime glass. A machine stamps the top of each bulb with the voltage, the wattage, and the company logo. Opaque light bulbs are simply clear bulbs with an inside coating of synthetic silica, a white powder. The coating machine charges the bulbs to 30,000 volts. Combined with just the right amount of heat, this electrical charge makes a thin layer of powder cling to the glass. A series of flames evaporates the moisture and breaks off any impurities. As the two production lines merge, a bulb goes over each mount. Torches then fuse the flared end of the mount to the neck of the bulb. Arms move in and mould the neck to fit inside the bulb's aluminium base. The next machine vacuums out all the air in the bulb and replaces it with pressurized argon gas. This inert gas will resist heat buildup, helping the filament last longer. After bending the lead wires out of the way, torches melt and seal off the glass exhaust tube, locking the argon gas inside. The bulb would now be fully functional if connected to an electrical current, but it needs a base in order to screw it into the socket of a light fixture. The base is made of aluminium. This machine inserts one of the bulb's lead wires through the middle and solders it in place. It then spot welds the other wire to the side. The result? Two base contacts to line up with two socket contacts. On their way to packaging, the bulbs undergo what's called flash testing, repeated light-ups using a higher voltage each time. This strengthens the filament inside, making it less likely to break during shipping. The bulbs are repeatedly tested. One last illumination to make sure nothing broke between flash testing and packaging. The automated packaging equipment handles the fragile bulbs with care. It's designed to have a light touch. So, whether you're looking for a party essential or a funky design for your living room walls, or perhaps you're just too lazy to cut up your own spuds, now you know how it's made. Today on How It's Made. Matches. This factory brings a little light relief. Carousel horses. Surely the main attraction. Fine porcelain. China that's not made in China. And car fuel tanks. Fill her up. But first, a predecessor of the modern match, a stick made of pine wood impregnated with sulphur, was developed in China in 577. The first friction match was invented in 1827 by English chemist John Walker. These matches could be violent, and the smell produced by the burning was unpleasant. Today's matches are strikingly efficient. Gone are the days of dodgy matches and nasty nifs. Today's matches are safer, and any smell dissipates in seconds. To make matchsticks, this company uses recycled paperboard, which is inexpensive and thick enough to support the weight of chemicals on one end. A stamping press partially cuts the paper, creating stamps. As can be seen in this view from inside the machine, a die first cuts the stems. Then a blade slices through the sheet widthwise, making strips of 120 stems each. At actual speed, it's just a blur, as the press makes nearly 500 strips per minute. Next, the strips move through a bath of hot wax. The wax soaks into the stems to about 1/3 of the way up. Then they dry in an oven for 15 seconds. When a match is lit, the wax slows down the burn speed of the chemicals, sustaining the flame for 4 or 5 seconds. Those chemicals are gelatin and silica to bind the chemicals to the stick, potassium chlorate and animal protein for oxidization, sulfur to fuel the flame, and 2 fillers. The chemicals are mixed in a large vat with hot water. This 317 kilo batch is enough to make the chemical batter for 25 million match heads. A conveyor runs the matchsticks through the batter to coat their tips. 3 rollers in the tank raise the surface of the batter. The first 2 ensure the front and back of the heads get covered. The third rotates faster to remove excess batter as the heads leave the tank. From there, the matchsticks travel a distance of 365 meters, while fans air dry them. The factory temperature is a comfortable 22 degrees Celsius, perfect conditions for the chemicals to dry and harden. These minerals are silica and red phosphorus. Add a little glue and you've got friction, the material in the strip you rub the match against to make the head ignite. To make these striker strips, as they're called, a steel wheel rolls friction onto paper that's moving through a cutting press. This isn't the same paper from which the matchsticks are made. It's a higher quality non-recycled paper, suitable for colour graphics, because many clients order custom printed matchbook covers. Another press with rotary blades slices through the paper, creating segments that are 10.7 centimetres long. That's the length of an unfolded matchbook. Now back to the matchsticks. The strips are arranged into double layers. A conveyor then feeds them into a machine that'll attach them to the matchbook covers. The machine performs several tasks. It cuts the matchstick strips into rows of 10 matches each. And it cuts the matchbook covers to their final width of 3.8 centimetres. The machine folds the matchbook covers over 2 rows, or 20 matches, then inserts 1 strong staple through all 4 layers. Next, a conveyor moves the assembled matchbooks to another machine that counts them and creates 2 side-by-side rows of 25, ready for boxing. This company also makes its boxes out of recycled paperboard. Each one holds 50 matchbooks. This is one factory where strike action is always welcome. In Britain, carousels tend to rotate clockwise. In the US, they turn anti-clockwise. Historically, carousels included a whole menagerie of animals, including dogs, cats, rabbits and pigs. But the star of the carousel is still the horse. Their life revolves around a fairground, but they're born here, on paper. A craftsman draws a pattern of the horse's silhouette, then fills it with a saddle, straps and a harness. Some models may include a shield, a coat of arms, or even flowers. Another craftsman then glues together blocks of linden wood. It's lightweight and easy to carve. He stacks 4 of them to create what's called an end block. It'll form part of the horse's body, what's known as the core. He clamps the blocks together to compress them and lets the glue set for 45 minutes. The finished core includes 2 end blocks sandwiched by top, bottom and side panels, plus 1 wooden piece which will later be carved into a saddle. The middle of the core is hollow. On a carousel with 50 horses, this trims the overall weight by up to 3 tons. After covering the core with carbon paper, the craftsman lays the pattern on top. He traces the pattern with a leadless pencil called a stylus. The carbon paper underneath transfers the drawing onto the wood. He'll follow these lines to cut out the basic shape of the horse. Most of the finer details will be carved later by hand. Using a bandsaw, he slices the core carefully along the lines. Next, a hole is drilled for the pole that attaches the horse to the carousel. Here, a craftsman uses what's called a carving duplicator to create the head. Following a template, the machine sculpts a block of wood into a horse's head, a painstaking process that takes 90 minutes. The duplicator can carve up to 4 heads at once. It also adjusts to carve some finer details into the larger pieces, such as the core. They use a parting tool to shape the decorative tassels on the bridle. This one has a fanciful Arabian-style design. The craftsman has many tools at his disposal to create all kinds of special features, such as a flowing, wind-blown mane. The tools are sharp, and they're precise enough to sculpt tiny, intricate parts, such as eye sockets, nostrils and teeth. Polyester adhesive putty is applied to the eye sockets, and 2 glass eyes are added. Unlike real horses' pupils, which are oval in shape, these are round, to create a friendlier look. This carousel horse is roughly half the height of a real horse, but its feet are life-size, so workers attach authentic iron horseshoes. These prevent the wood from chipping under the feet of riders who get rowdy in the saddle. Wooden pegs temporarily connect the head and tail to the body. Once the alignment has been checked, the sections will be glued together. After the entire surface has been sanded down, the paint job begins. First, 3 coats of white primer. This highlights any imperfections the sanding missed. Once that's done, the artwork begins. This horse will wear a bright, multicoloured harness. Its coat will be in different shades of the same colour for a realistic look. It can take up to 5 coats of paint to get it just right. Up to 7 coats of varnish will keep the horse looking beautiful for decades. After 2 months of work, assuming there was no horsing around, these striking creatures are ready to make their rounds. Coming up on How It's Made, fine porcelain. No bulls allowed in this factory. And car fuel tanks. You'll be a fool to miss it. See you after the break. Porcelain is used to make crockery, kitchenalia, sanitary wares and objects of fine art. Its resistance to the passage of electricity makes porcelain an excellent insulating material. It's also used in dentistry to make false teeth. Porcelain is often called China, after the country that invented it more than 1,200 years ago. This company makes 40 different porcelain items. It It all begins with a sketch of the piece, in this case, a teapot. A master mould of the piece is created, a negative made of plaster. Craftsmen use it to make a production mould. Porcelain begins as a powder, a blend of 3 minerals, quartz, kaolin and feldspar. This powder is mixed with water to make a wet paste called slip. The mould is filled with slip. Within 10 minutes or so, the porous plaster absorbs the water, leaving a crust of hardened slip. The rest is poured out. After another 30 minutes, the crust has hardened further and the mould can be peeled away to give the first glimpse of the teapot. Excess crust is removed from a different mould for the spout. It's then left for about 10 minutes until it's hard enough to handle, but still soft enough to sculpt. A utility knife is used to open the end of the spout. The edges are smoothed out using a little water and a sponge, and the rim is curved. Next, the handle is extracted from a third mould. Then 12 holes are pierced in the spout side of the teapot to filter out the tea leaves during pouring. Some slip is brushed on to attach the spout and the handle. This model has a wedge along the collar to help align the handle correctly. Other designs have small notches instead. More slip is brushed on to ensure the parts will bond. And the surrounding surface is sponged to smooth out the drips. The piece dries for 2 more days before the lines along the handle and under the spout are carved away and the rim is sanded down. Some pieces are made using a pressure casting system. The mould is made of resin and tiny polyester beads that create pores which absorb the water in the slip. After a hydraulic press closes the mould, the machine injects slip into the cavity. 12 minutes later, a craftsman uses a suction plate to remove what will become a serving platter. He places the piece on a plaster block. The porous plaster lets the underside dry without leaving marks. The items are fed into a large kiln which heats up gradually, taking 8 hours to reach a searing 1000 degrees Celsius, and takes 12 more hours to cool down. Firing hardens the porcelain and enables it to better absorb a coat of enamel. After brushing off any dust, the craftsman dunks each piece in enamel, a protective coating. The porcelain absorbs it right away, and this glaze turns into a shiny skin once the pieces are fired again. Each piece is handled in a particular way to avoid leaving drip marks. During a second firing, the air in the kiln is carefully controlled to produce a pure white porcelain. Reducing the oxygen level removes any undesirable colours. This time the temperature is even higher, 1400 degrees Celsius. The pieces shrink by around 15%. After a quality check, the company logo is added. The transfer bonds when the plate goes back into the kiln for another 12 hours at 850 degrees Celsius. In the end, the porcelain is translucent enough for light to shine right through. Other pieces offer more illustrated displays for a truly fine dining experience. Worldwide, 60 million petrol tanks are made each year for new vehicles, and millions more to replace old or damaged tanks in existing cars. And considering how much it costs to fill them, it's no wonder today's petrol tanks are made to be tough. Making a petrol tank begins with a simple sheet of steel. It's nickel-plated to make the tank rust-resistant. The steel is placed in a hydraulic press that applies 800 tons of pressure. This compresses the sheet between two dies that shape the bottom half of the tank. The press forces the male die up against the sheet and into the cavity of the female die. To make the top half of the tank, or tanks of a different size, it's simply a matter of changing dies. On the tank's top section, a stamping press imprints information, such as the product and lot numbers and the manufacturer's name. A hydraulic punch then pierces two holes, one for a tube to fill the tank and another to vent it. This machine makes an opening for a component called the Fuel Delivery Module, or FDM, which will send fuel to the motor. A conveyor moves as many as 180 top sections per hour to the next production phase. There, a steel and nylon jig is used to install a steel ring that'll position the FDM. The ring is spot welded in 6 spots to fuse it to the top section. 2 notches on the ring will align the FDM properly. The top and bottom sections are tacked together and properly aligned for the comprehensive welding that follows. 2 metal wheels compress the sections together and water cools the area, as a machine called a seam welder fuses the upper and lower halves of the tank. Steel tube is fused to the tank using a gas torch and lead solder. This is the filler tube, into which you insert the nozzle when you fill up at the pump. Fuel flows in, and air vents out through the tube simultaneously. A sensor automatically shuts off the petrol pump when the air pressure inside the tube reaches a certain point. Most tanks fill to only about 80% capacity to leave room for vapours caused by hot weather. Robots weld the tanks destined for brand new vehicles because the work has to be precise and consistent in order to aid the assembly line robots at the car plant. The human welded models are sold to auto repair shops as replacements for damaged tanks. They don't require the same precision because a mechanic does a custom installation. When the robots finish welding the tanks, they transfer them to a conveyor belt that moves them to the next production phase. There, a tin-plated venting tube is attached. Tin makes it rust resistant. A steel component called a baffle is added to the bottom section of the tank. This reduces the sloshing of fuel inside the tank, resulting in less noise for the driver and less metal fatigue for the tank. They're usually just for tanks found in larger vehicles. The top section is now placed onto the bottom section, and a hose is pulled through the opening in the top. This hose will connect to the FDM. After a welding machine fuses both halves together, another machine bends the sides downward. This gives designers extra space to work with. Each tank is tested for leaks by being immersed in water. All the holes in the tank are blocked and a little extra air is pumped inside. Bright lights aid the search for any bubbles in the water. If air can escape, so can petrol. No bubbles and the fuel tank passes inspection. Only then is it ready for shipping and a starring role in your car. So, whether you're looking for a superior spark, or perhaps a touch of equine elegance, or maybe you need some cracking crockery, now you know how it's made. Today on How It's Made. Glass cookware. We blow the lid off this story. Soap bars. We'll come clean with all the details. Steel drums. How it's made goes Calypso. And firefighter uniforms when safety's a burning issue. But first... The idea of Pyrex was cooked up by the wife of a glass industry scientist in 1913. She believed the tough glass used in lantern globes would be great for baking cakes in. So, she baked one in some glass her husband brought home. The cake was a hit, and the notion that glass was too fragile for the oven was shattered. Today, you'll find glass cookware of various shapes in most homes. A true recipe for success. A batch feeder pushes ingredients into a large furnace as they spill out of a bin overhead. Silica sand is the main ingredient of the mix. It's a crystalline substance which makes glass transparent. The batch also includes soda ash and recycled glass. Some of the other ingredients are a trade secret. The furnace heats the mix to its melting point, over 1,500 degrees Celsius. It turns into molten glass. The glass in this lava-like form will spend up to 24 hours in the furnace. On its way out, mechanical shears cut it into gobs. The gobs slide down a water-cooled chute and drop into a baking dish-shaped mould. There are 16 moulds on a rotating table. As it turns, the table delivers the gob-filled moulds to a plunger, which presses them into the baking dish shape. Continuing to rotate, the table positions the moulds under blowers. They cool the freshly moulded glass so it holds its shape. A mechanical arm suctions up the glass dish and sets it down on another revolving table. Flames lick the glassware from burners above and below. The dish is exposed to a temperature of over 1,000 degrees Celsius. This softens its sharp edges so that the rim is smooth. Next, hoses blast high-pressure air, cooling the dishes to solidify them so that a mechanical arm can pick them up without misshaping them. It transports the glass dishes to a conveyor belt. Further down, another arm feeds the dishes to a kiln, where heating and cooling cycles temper the glass. This is what gives the toughened glass its strength. Now it's time to put a lid on things. A different plunger presses glass gobs into a lid shape. Every good lid should have a knob. So, a valve inside the mould forms one, and then thrusts the lid upwards to be picked up by a mechanical arm. The arm flips its lid and sets it down on a conveyor belt. The lids are on the move, travelling through a tempering kiln. On their way out, a fan cools them off so they can be handled, this time by human hands. Each glass lid is inspected before it's packaged. On another line, there's a product that's made to measure. Small platforms lift the measuring cups to suctioning arms that protrude from a revolving silkscreen machine. A squeegee forces enamel through a screen, printing measurements onto the cup. Over in the lab, this sample dish is being roughed up. Rubbing it with sandpaper mimics years of wear and tear, but it's about to be subjected to even more abuse. sharp tool is placed in the centre of the dish before it's time for the hammer test. Will it break without shattering into numerous little shards? It's a clean break, which means this dish has met the quality standards. Smashing. Or to put it another way, this glass has plenty of class. A formula for soap made from water, alkali and cassia oil was written on a Babylonian clay tablet around 2200 BC. Manufactured soap bars first became available in the late 19th century, and advertising campaigns helped to increase their popularity. This product's reputation is squeaky clean. It has function and form. Soap comes in a variety of shapes, colours and textures. It all starts in a bubbling kettle, where animal or vegetable fat reacts with sodium hydroxide, a caustic substance, to create soap. Water is added to keep it fluid, as steam bubbles up through the centre to mix it all up and encourage the chemical reaction. The leftover soap that settled at the bottom of the kettle is poured into a tank and reused in the next batch. Now, hot liquid soap is sprayed onto a big metal roll. It solidifies in a flash, and a large blade scrapes it off the roll, creating ribbons of soap. The soap ribbons plunge into a hopper, where an auger moves the soap along, sending it down a chute. The soap ribbons fall all the way to the next floor, to big steel rollers called mills, which mix and compress the soap. A blade scrapes it off the rollers and cuts it into ribbons again, but these soap ribbons are denser. Inside the next hopper, another auger turns. It pushes the soap through an extruder called a noodle plate that shapes it into soap noodles. As the noodles fall from the extruder, they're collected in bins, which are then dumped into a mixer. At this point, colour is added, in powder and liquid form. Steel blades stir it up until the colour coats the soap noodles. Fragrant oils are added, and the blades toss it all together. When the batch is ready, a trap door opens. The blades keep turning, nudging the soap out the door. Then it's forced through another noodle plate. This mixes up the batch a little more. Next, the soap is pushed through a forming plate, making a long bar. Blades mounted on a track slice it into shorter pieces called slugs. The soap slugs move to the next stage on a 2-lane thoroughfare and head into a die press. A mechanical arm pushes the slugs through an oval plate, trimming it and then loading it into the die. The die rotates to accept the slugs. Mechanical presses move in to shape and stamp them. Mechanical arms suction the bars to remove them from the die. These mechanical pushes help. They nudge the soap bars out of the die towards the suctioning arms. The oval soap bars now travel through a wrapping station. A blade crimps and heat seals the plastic wrap in one swift movement. Then, automated grippers grasp the wrap bars and load them into a machine, which slides them into boxes. Now it's time to pack it in and scrub up with the soap of your choice. Don't forget to wash behind your ears. Coming up on How It's Made, steel drums. These instruments are sure to be a big hit. And firefighter uniforms. If you can't stand the heat, then get one of these. See you after the break. The story of the steel drum begins in Trinidad in the 1930s, when street band skirmishes led to the banning of skin drums. So people improvised and made drums from thick bamboo poles, car parts, tins, and finally, oil barrels. They came up with a whole new sound without skipping a beat. When people first started pounding on steel instruments, they inadvertently dented them. That's how they discovered that each dent produced a different pitch. So now steel drums are dented on purpose. To make a drum head, a circle is cut from a piece of steel. A metal ring is welded onto it, and then a metal shell or skirt is positioned on the ring and welded in place. The drum is held in a clamp, and the exact center of the drum's head is located. A measuring guide is put into place and used to mark radial lines from the center to the rim. Each line is 10 degrees apart. As the drum turns, circular lines are drawn, forming a grid. The head of the drum is pounded with a pneumatic hammer, while the grid is used as a guide to ensure the work is done evenly. It takes 8 hours of hammering to transform the drum into a bowl-like shape. This is called sinking the drum. Then, with a special guide for curved surfaces, a technician measures out another grid. He outlines the notes that are about to be hammered out, in this case a high B and an E. Then, he hammers down the steel around each one to shape the note. Getting this right takes skill and a lot of time, up to 50 hours. He trims the drum skirt to the correct length and tapes a stencil of the company logo onto the skirt. This device is an electrical etching machine. It uses acid and electrical current to eat away the steel exposed through the stencil. This technician is using an ultrasonic thickness probe. It's pressed against a note. Using high-frequency sound waves, the probe measures the steel's thickness to within a fraction of a millimeter. The notes are ground down where needed. Using a scribing tool, the technician scratches a line around each note so it will be visible to the player. To tune a steel drum, another technician plays a note with a stick and then dents it with a hammer to adjust the pitch. He hammers the note until it sounds right. Occasionally, he turns the drum upside down to knock out a note from the underside. For the fine-tuning, he relies on an electronic tuner. A microphone delivers the sound to it, and the lines on the screen indicate whether the note is in tune or not. The border of each note is burned using a blowtorch, then cooled down with water. The process tempers the steel, making the notes more resonant. The drum is tuned again and checked for flaws. This particular make of drum is chrome-plated before it's tuned for a final time. It's taken 120 hours to make this steel drum. At last, it's time to take a break and party to the steel band sound. Firefighters have been doing their jobs heroically for centuries. Their uniforms, however, were not always up to the task. Today's firefighters, though, are cloaked in layers of space-age material. The protective armour has virtually eliminated firefighter deaths caused by burn injuries. A computer-guided machine cuts out more than 90 parts to make the outer shell, just one of 3 layers that make up these firefighter jackets. This fabric contains a synthetic fibre known as PBI, which can protect against temperatures higher than 600 degrees Celsius. Another machine tapes the seams of the jacket's middle layer, the moisture barrier. Pressure rollers and heat activate glue in the tape, sealing the seams. This synthetic fabric lets perspiration through, but blocks some harmful liquids such as battery acid, hydraulic fluid, or infected blood. Now the moisture barrier is lined with the thermal liner, the jacket's third and innermost layer. This synthetic fabric protects against temperatures of over 400 degrees Celsius. To reinforce them, the cuffs, hems and front and back panels are sewn together with heat-resistant tape and thread. But the neck area is left unattached, so the firefighter can pull the jacket inside out to inspect the liner between rescues. Back to the outer shell. 2 orange and silver stripes are sewn to the front and back panels. A stripe is also sewn onto each sleeve. The fluorescent orange makes the firefighter more visible in daylight. The reflective silver is for nighttime or in smoky conditions. In some cases, reflective die-cut letters are added, identifying the fire department or spelling the firefighter's name. A strip of Velcro goes onto the left front panel. It's one of 4 ways to fasten the jacket, in addition to zips, poppers and hooks. To keep water from entering through the front of the jacket, a strip of the same fabric used to make the moisture barrier is attached. It's sewn inside the outer shell's right front panel, known as the storm flap. The storm flap's other side gets a Velcro strip that mates with the Velcro on the left panel. The front panels are attached to the back panels. The garment is folded over and the machine sews through the 2 layers at once. It's another way to reinforce the seams of the jacket. A different sewing machine is used to attach the sleeves. 5 different seams are sewn to join the shoulder areas. This is critical because the firefighters will be carrying an 11-kilogram air tank on their backs. The seams spread out the stress this weight places on the jacket. 3 metal poppers are attached to the inside front of the outer shell. These will attach the outer shell to the 2 inner layers. Then, a heat-resistant plastic zip is added. This machine applies 3 rivets to each of 4 spring-loaded hooks along the right front panel of the jacket. A 1.8-metre-long strap cinches around the armpits to drag an injured firefighter away from danger. The assembled inner layers are snapped together with the outer shell. There are 4 poppers on each cuff, which could heat up quickly in a fire. Tabs ensure they never burn the firefighter's skin. The front panels come together with 4 poppers on each side. The 10-centimeter collar unfolds, covering the neck where it meets the firefighter's helmet. This testing device gauges how long it would take to sustain a second-degree burn. A gas burner shoots a flame that's over 1,000 degrees Celsius directly onto the jacket's outer layer. A sensor mimics human skin sensitivity to heat. The material fails the test if the transferred heat would cause second-degree burns in less than 17.5 seconds. Finally, the uniform is showered for 20 minutes to test its watertight seal. The dummy is wearing a cotton bodysuit underneath. Just one wet spot on that bodysuit and the uniform fails inspection. So, whether you're looking for a better method of baking, or hoping to smell just a little more sweet, or perhaps it's the sound of carnival you're after, now you know how it's made. Today on How It's Made. Crayons. We draw your attention to this colourful report. Wooden kayaks. We'll see what keeps this business afloat. Lawnmowers. The grass is always greener at this factory. And gold chains. From the production line to the neckline. But first, it's hard not to wax lyrical about crayons. They were invented in America in 1903, when a non-toxic version was created from the basic wax crayon already used for marking crates and barrels. We take a look at how colour is added to childhood. These crayons are made from a combination of waxes, primarily paraffin, which is ideal because it's inexpensive and easy to melt. It also has what's called a nice rub-off, meaning it leaves enough wax on the paper. The wax is melted to 62 degrees Celsius. Then a secret powder is added to strengthen the crayon and act as a filler, boosting the number of crayons the wax will produce. Various synthetic chemicals are also added. There's one to keep the wax from sticking to the mould, and a fatty acid called stearic acid to improve the rub-off. Now the wax is tinted. In this case, the addition of yellow and red produces orange crayons. This factory can produce 127 different colours. Every ingredient in the crayon is non-toxic. After adding more wax, the mixture is blended for about 45 minutes. Now the wax is pumped into this device, called a rotary machine. It first injects the wax into crayon-shaped moulds. Then, it envelops the moulds in cool water, hardening the wax within 60 seconds. As the moulds continue along the circuit, a blade scrapes off the excess, which gets recycled. Just one rotary machine moulds more than 2,700 crayons per cycle. With several machines operating simultaneously, this factory churns out 30,000 crayons every hour. The machine ejects the crayons. and a conveyor transports them to the labelling machine. One by one, they drop into the grooves of a revolving drum. At the bottom left, glue coats the surface in between the grooves, just before the crayons go in. The machine then slaps a label onto each crayon. A roller presses the label against the adhesive. Then a small arm wraps it around the crayon. This machine labels 8,500 crayons per hour. The crayons exit the labelling machine and land in a box. They're sorted according to colour into the appropriate hoppers of the packing machine. The packaging line is entirely automated. The factory programs the machine to collect a certain number of crayons in specific colours, according to the type of pack in production. Their best sellers are packs of 16 and 24. The packing machine is designed to handle the crayons gently. Occasionally, though, a crayon does crack or a label comes loose. When that happens, a sensor automatically stops the machine and a light goes on above the problem hopper. The jam is cleared, then production resumes. Once the count is complete, the crayon line and the box line meet. A pushing device slides each set of crayons into a box. A built-in scale weighs every box. Should one be underweight, the machine automatically blows it off the conveyor belt. Then the missing crayon is added manually, ensuring a full complement of colours for every budding artist. For thousands of years, people in the Arctic have used kayaks to hunt, and for good reason. These slender vessels glide swiftly in the water and are light enough to carry. High-tech materials make today's wooden kayaks more durable than ever, yet still a glorious way to slice through the water. This construction begins with plywood, made from a kumi, a rugged type of mahogany. A computer-guided routing machine cuts out the boat's various parts. One has finger joints that interlock with another piece to make one long strip. These panels will cover the sides of the vessel and most of the top. The planks are only 4 millimeters thick. The entire kayak will weigh just 17 kilograms. These are bulkheads, end panels, footrests, and curved pieces to support the deck and sides. After applying 2 coats of epoxy resin, a craftsman assembles the parts and secures them in a jig for 6 hours until the glue sets. The side panels will span the entire length of the boat, which is just over 5 meters. Assembling the kayak is pretty straightforward, so if you want to save money and do it yourself, you can buy this kayak cheaper as a kit. The end panels are planed and sanded to create a curved tip. Small holes, spaced 12 centimeters apart, are drilled along the edges of the bottom panels. Then, copper wire is threaded through the holes. This stitches the panels together temporarily, keeping them flexible and thereby easy to assemble for gluing. Wooden pegs are placed between the side panels to pry them open. Then those panels are joined with 2 screws in the front and 2 in the back. At this stage, the kayak is upside down. The bottom panels are added. They're attached using copper wire, which won't stick to the resin used to glue these parts together. After the boat is flipped, a bulkhead is added using more wire. Using a putty knife as a gauge, the craftsman ensures the gaps at the seams are even. Then he flips the boat and coats the seams in resin. It's left to dry for 6 hours, just part of the 40 hours it takes to build the kayak. Before the glue hardens, the top of the boat is checked to make sure that it's level. The pieces can be adjusted if need be. After the wire is removed from the seams, more resin is applied to these areas. Over this, strips of fiberglass cloth are placed to form a watertight seal. 3 more coats of resin will also be applied throughout the inside of the kayak. Once it dries and the entire surface has been sanded and varnished, the footrest assembly is added. This one's got pivot pads with cables that control a rudder to help steer the boat. This is an optional feature. Next, resin is applied along the kayak's upper rim. The top panel is added to form the deck. Then, the entire boat is wrapped in packing tape, which compresses the panels as the resin sets for 12 hours. These pieces form a raised rim around where the kayaker sits. A waterproof skirt fits under this rim, keeping the area dry in the water. The deck gets 2 coats of resin. An hour later, fiberglass is spread over the bottom to seal and protect the wood. The bottom then gets 3 coats of resin. Next, up to 6 coats of varnish are sprayed on, depending on the type of finish the boat will have. This protects the wood from sun damage. A foam backrest is added, and then a seat. And finally, flexible rubber straps for securing your harpoon or your paddle, so you don't get caught up a creek without it. Coming up on How It's Made, lawnmowers. This one will be sheer delight. And gold chains, a factory with the Midas touch. See you after the break. A gardener's job became much easier in 1830 with the invention of the first mechanical lawnmower. Nowadays, most lawnmowers have electrical motors or petrol engines. They turn blades that are either on a reel and cut like scissors, or rotate like a propeller to chop the grass. Cutting-edge technology. These petrol mowers have rotary blades that spin horizontally on a vertical crankshaft. To make the blade housing, which is called the deck, a machine first applies a lubricating chemical to sheet steel, which was coiled when it came to the factory. The chemical helps flatten it, so it's easier to cut. A press then perforates the sheet every 60 centimeters. After the press separates the segments and rounds off the corners, a robotic arm moves each segment onto a die. A 500-ton press bends the steel like tin foil in between 2 molds to give the deck its basic shape. A robot lifts the oily decks with suction cups and moves them to another press. This machine trims away the excess around the deck's edges. Another machine bends the sharp bottom lip inward to make the deck safer to handle. The factory uses robots because they work faster than humans, processing 500 decks an hour. After a thorough cleaning, the decks move to an electrostatic paint booth. The powder paint is laced with a negative electric charge, the decks with a positive one. This draws the paint particles onto the decks, creating a thorough and even coat. The factory's 6 paint booths are on tracks, so when it's time to change colour, the entire chamber can easily be switched for a clean one. The paint cures at 190 degrees Celsius for 15 minutes. This press bends 2.5 metre long tubing to form the mower's upper handle. Another press bends 1.8 metre long tubes to make a shorter lower handle. Later, the two handles will be attached to form one folding handle. Because it folds, it takes up less space in the shipping box and later in your garage. Here's the mower's 5 horsepower engine. It's attached to the deck with 3 bolts, using a powerful torque gun so that vibrations won't cause the bolts to loosen. Later, the blades will be mounted to the engine's crankshaft that protrudes through an opening in the deck. Next, a plastic rear door through which the grass clippings eject is installed. This door attaches to brackets which have levers that adjust the mower to 9 different height positions. The plastic rear wheels are mounted. Next, an adapter is added to stabilize the blade on the crankshaft. Then the blade, which is wider at each end to create the correct airflow inside the deck. The blade is secured tightly with a powerful wrench because it's going to spin at 3,300 revs per minute. The front wheels are 1/3 smaller than the back ones. This makes the mower easier to maneuver over uneven terrain. Rubber covers are put on the height adjustment levers, so they're softer on the fingers. The mower adjusts from 2.5 to nearly 9 centimeters off the ground. The lower handle is secured. Then the upper handle is attached to the lower one. The consumer can tighten this after shipping. A safety handle is added. This turns the engine off if the gardener is not squeezing it against the upper handle. Finally, labelling is applied to indicate the mower's horsepower and width. Now you can fill her up and she's ready to cut your lawn down to size. Some of the first gold chains date back to the ancient cultures of Iraq and Greece. They were symbols of wealth, royalty, and the divine. Luckily for us, jewelers now make these personal treasures more affordable and more durable than ever. In this factory, all that glitters is gold. Pure gold is fairly soft and bright yellow, so it's common to create an alloy to strengthen it and alter its colour. Copper lends a reddish hue, and brass helps the alloy melt more quickly than gold and copper would alone. Depending on the ratio, adding these metals produces 14 or 18 karat gold. The mix is melted in a crucible at more than 1,000 degrees Celsius. Just 3 of these scoops are enough to make about 5,000 14 karat gold chains. The molten alloy is poured into a casting machine. Water cools the metal to around 370 degrees Celsius, solidifying it. The metal passes through a round die, which shapes it into a golden rod that's nearly 2 meters long. After the rod is cut in half, it's passed through what's known as a breakdown mill. The machine reshapes the rod from circular to square, so it will be easier to stretch. The next stop is called a tandem mill. It has 12 rollers that stretch the rod until it's as thin as a piece of spaghetti. As it emerges, rollers shape the rod into a coil that's 24 meters long. The coiled metal is softened in an oven. Then what's now a wire is uncoiled and continues to stretch as it's passed through a die lined with industrial diamonds. To prevent overheating, the machine sprays lubricant to cool the wire while reducing it to the width of a human hair, its final size. The wire then winds into a spool, almost 3 kilometers long. Next, 32 of the spools are unwound, and the wires are run through another oven which softens them further. Just in case you're thinking working here is a golden opportunity, you should know that security is very tight. Employees must pass through metal detectors before going home, and wearing jewellery to work is strictly forbidden. This machine makes what's called cable chain. It passes wire through a link and closes it to make another link. The machine makes 600 links per minute. Here, a random quality check is being carried out. This machine makes a Venetian-style chain. The wire passes through a channel, where mechanical jaws bend it over a die to make a link with the preceding segment. To make what's called a spider style, this machine passes a wire through up to 5 loops before closing the link. For a Figaro style chain, this machine makes 3 short links before a mechanical arm moves the chain to another area to add 1 longer link. The arm then moves it back to add 3 more short links. The simplest style is known as a rope chain. To make it, this machine threads a wire through, then closes it to make another loop. The finished chains are coated with a lubricating powder that prevents the links from sticking to each other during the next step, when the chains are heated to 815 degrees Celsius. This activates a soldering agent, which was added to the metals earlier. It fuses the ends of the links to each other. This machine welds a link to a clasp on the chain. A tag indicating the gold quality goes onto the clasp. Finally, the chains go through 4 chemical baths, which clean them thoroughly. Then they're plated with a layer of 14 or 18 karat gold, which creates a more vibrant finish. After one last quality check, these chains are ready to dazzle their way to a neckline near you. So, maybe you're looking to add a little colour to your life. Or something like this floats your boat. Or perhaps you're looking to create the ultimate manicured lawn. Now you know how it's made. Today on How It's Made. Inflatable safety devices. We really go overboard with this one. Braille typewriters. Connecting the dots. And carbon fibre cellos. Making them is a noteworthy endeavour. We'll have a special 2-part report. But first... They're designed to keep your head above water. Inflatable safety devices activate in seconds and keep you afloat until help arrives. You'll find these survival devices on aeroplanes and boats. Even when they're not inflated, they're a great help, because just knowing that they're there makes you feel safer. To make a life jacket, a computer-controlled knife cuts a pattern in urethane-coated nylon. Heat from the blade makes some pieces stick together, so a worker peels them apart. This shiny side is the waterproof coating. It will be on the inside of the life vest. The front of the vest is placed on a vacuum table to hold it down. Then the correct amount of carbon dioxide needed for inflation is silk-screened onto the fabric. Next, an oral inflation tube is pulled through a pre-cut hole. And then the assembly is placed under a radio frequency press. It emits energy that heat seals the tube to the fabric. The front and back vest pieces are fastened on pegs to align them. The table with the vest pieces is also slid under a radio frequency press. Again, electromagnetic energy bonds the plastic pieces. This vest has been put together without a single stitch. The cylinder that contains the carbon dioxide has been installed. It holds 33 grams of the gas under pressure, which will instantly inflate the vest with one tug on the tap. It also activates automatically when immersed in water. A small tablet inside dissolves, triggering a spring that punctures the cylinder. Pull a cord on this pack and you have an instant lifeboat, complete with a roof. To make one, the computerized blade cuts shapes out of rubberized fabric, while a plastic film helps hold it in place. A rubber adhesive is brushed on to seal the boat's joints, and rubber tape is pressed over the glue. Air bubbles are removed. It will take several days for the bonding to be complete. The same rubber adhesive is applied to all the inflation valves and pressure tubes. The glue is wiped with a damp rag to help activate it. Then a valve is inserted through a hole in one end of the raft's air chambers. More glue is applied to the outside around the valve and secured with a ring called a doubler. More rubber adhesive is applied onto the lower inflated chamber. Then a sheet of rubber flooring is stretched over it. The edges are smoothed down, again to remove air bubbles. Rubberized tape is run around the rim. It will protect it and also act as a hinge between the floor and the upper air chamber, which will go on next. In preparation for that, measurements are made to align all the inflation valves. Then, the upper air chamber, which forms the walls of the raft, is pulled on top of the floor and lower chamber. The valves are lined up, but not connected yet. Next, regular air is pumped into the upper chamber to test the shape and function. A plastic strip has been keeping the glued surfaces from contacting. Now it's pulled out and pressure is applied to initiate contact. Before the raft is packed, the entire survival kit is checked. There's the first aid package, mini flares, food rations, a pocket knife, and bags of water. Enough to keep you from getting that sinking feeling as you float around waiting for help to arrive. The Braille system is based on 6 dots arranged in a rectangle, 3 dots high by 2 dots across. This is called the Braille cell. Different configurations of dots within this cell represent different letters of the alphabet, numbers, and punctuation marks. Clever stuff. A Braille typewriter has a space bar in the middle and 6 keys, one for each dot of the Braille cell. Pressing a key makes a pointed steel rod called a stylus type a raised dot. To build a Braille writer, the 6 styli are positioned one by one in a carriage, with steel spaces in between. The spaces ensure each stylus can move freely. A cover plate seals the back of the carriage, and what's called a stripper plate closes the top. The plate has 6 holes in the configuration of the Braille cell. When a key is pressed, the corresponding stylus protrudes and strikes the paper against the dot-shaped die, creating a raised dot. The die is screwed to the carriage top, but not yet installed in the machine. This is how the carriage and die will meet once it's in place. Construction of the components which move the various styli begins. The first part is a steel cam rod. One end of it has a small eyelet called a lug. A pin is put into it. Then it's slipped through holes in the prongs of a metal strip called a link. Later, the other end of the link will be connected to a lever attached to a key. The Braille writer's other components are made of cast aluminium. The left end plate covers the left side of the machine, so that the carriage tube is connected. This is the cylinder on which the carriage rides. And then the feed roller, the mechanism which is turned to feed a sheet of paper into the typewriter. Next comes the rear support, that assembly of cam rods and links. The carriage is slid onto the carriage tube. Next, the drum is installed. The feed tube transfers the paper to the drum. The drum winds it into the machine, positioning it for typing. Then the rack bar. Each tooth in it is the width of a Braille cell, ensuring the carriage advances the correct distance between letters. The chain assembly which advances the carriage is installed. The other side of the machine is closed off with the right end plate. Now the process of connecting the parts that move the styli can be completed. So far, each cam rod connects to a link. Now each link is connected to a cam lever, then each lever is fixed to a key. Here is how it all works. When a key is pressed, it triggers the cam lever to turn the cam rod and pushes up the stylus. The stylus strikes the paper against the die, yet to be installed, and produces a raised dot. There's still one more paper feed component to install, the pressure roller. It holds the sheet of paper against the feed tube. Now the die is screwed to the carriage top and installed on a support beam. Then this assembly is positioned over the stripper plate at the top of the carriage. The paper hold tension is checked and adjusted. The back plate has slots for the 2 levers that adjust the margins. The apron goes below the keys, the front plate above them. Then the last component, the carriage lever. When you type to the end of a line, you push this lever to the left to return to the left margin. You also push a key on the far left to advance the paper to the next line. Typing on a Braille writer is an embossing process, so you have to use thick paper. Single keys and combinations of keys are pressed to produce different configurations of dots, each signifying different letters of the alphabet. Communication at your fingertips. Coming up on How It's Made, it's a How It's Made 2-part special as we take a look at carbon fibre cellos. Certainly sounds like a good idea. See you after the break. This cello is made of carbon fibre instead of traditional wood. Some believe this newer carbon version has a more powerful sound than the wooden instrument. It still has that characteristic sweetness, but is considerably louder. And after all, every musician wants to be heard. The carbon cello is the masterstroke of a Boston symphony cellist who noticed waves resonate loudly against carbon fibre bolts. The top piece of the cello is cut from fabric that's woven with carbon strands. This material is stronger than steel, yet electric shears easily cut through it. Numerous top cello pieces are cut out and then set aside while work continues on another section of the instrument. Special resin is brushed onto a fiberglass mould of the cello's back, ribs and neck. The mould has been pre-waxed to keep the resin from sticking to it. The idea is to saturate this large piece of carbon fabric with resin as it's tucked into the curves of the mould. It's smoothed down to get rid of any bubbles that could affect the cello's tone. More resin is brushed onto the other side of the fabric. Any surplus is sponged away. And then, to build a laminated carbon fibre shape, more fabric and resin layers are added. The layers are covered with nylon-like material, and the edges of the carbon fabric are trimmed. Next, perforated plastic is placed on the nylon, and absorbent batting is piled on top of that. A vacuum pump is installed, and a large plastic vacuum bag is draped over everything. Then the vacuum is activated. It sucks out the air and any excess resin. The perforated plastic controls the amount and the batting absorbs it. While it's still under vacuum, the whole thing is put in an oven to bake the carbon fibre layers together. After the batting and plastic are peeled away, it comes out looking like this. The layers have fused together, and the shell has a sleek look to it. The cello's top piece is laminated in a mould and baked until it's also hard. Using a bandsaw, the ragged edges are trimmed off and sanded for a smooth finish. Now the cello top piece is clamped onto a fixture that has stencils on the back. With a router, they cut out the stencil shape. The sound will eventually emanate from these F-holes. The company label is glued to the inside of the cello's back section. Then, glue is added around the top inner rim of the cello. The back is taped tightly in place while it hardens. Next, the laminated carbon fingerboard is glued to the neck of the cello. Holes are drilled into the peg box, and pegs which are used to tighten the strings are inserted. Soon, this cello will be more than just a shell. Coming up, they raise the curtain on its inner workings. The story of this cello has many layers. They're all carbon, and now the layers have hardened into the shape of a concert instrument. At this point, you can't make music with it though, because the inner workings have yet to be constructed. A process that's a carefully orchestrated performance. The cello frames need a bit of bodywork. They're roughed up with sandpaper. Then a polyurethane clear coat is sprayed on to protect the surface. Then it's over to the string specialist, called a luthier. He sets a roughly cut wooden bridge on top of the cello and measures the position. The placement of this bridge needs to be exact because its job is to elevate the strings and transfer their vibrations to the instrument. Using a grease pencil, the luthier maps out the position of the bridge between the F-holes and then sets it aside. Now he slips the wooden sound post into one of the F-holes and wedges it between the front and back of the cello. The sound post is crucial. It will strengthen the cello and couple the strings' vibrations between the front and back of the instrument. This is delicate and highly skilled work. He measures to determine if the sound post is on the mark. If it's off by even a millimetre, he adjusts it a bit more. Afterwards, he double-checks the bridge's position. Then, with a red grease pencil, he colours over the spots where the feet of the bridge are to sit. He presses the bridge's feet into the grease marks, and this makes red smears on the feet. The smears tell him where to shave the wood, so that it will fit perfectly onto the cello. The bridge doesn't get glued down. It's held in place only by the tension of the strings. Next, the luthier makes pencil marks on both tips of a measuring stick. He leans the stick against the bridge at the same angle as the strings that will run over it. He then transfers the pencil marks from the stick to the top of the bridge. He rounds off the marks by penciling around a template. And then he carves the bridge down to size. He planes it down to make it thinner. With a file, he cuts grooves to cradle the strings. Now, he moves to the bottom of the instrument and slides a spike called an end pin into a pre-cut hole. The end pin will rest on the floor, steadying the cello. He lassos the end pin with plastic rope, which is attached to the tailpiece. And he rests the tailpiece on the belly of the cello. He pulls the steel strings from the pegs and hooks them onto the tailpiece. Like most classical string instruments, the cello has 4 strings. Now, the strings are slid into the grooves on the bridge. The pegs are turned to tighten the strings. The strings push down on the bridge, holding it in place. Then the cello is tuned, and it's now ready for a full-scale performance. So if you've got that sinking feeling and you're looking for a way to stay afloat, or perhaps this is the type of thing you're after, or maybe you're just looking to make a sound investment, now you know how it's made. Today on How It's Made. Carbon fibre masts. Making these is a tall order. Fortune cookies will bring you words of wisdom from the assembly line. IMAX projectors. Making them is quite a show. And roller chains. We'll tell you about their many strong points. But first, in the world of sailing, lightweight ideas are the best kind. This carbon fibre mast is a good example. At half the weight of aluminium or wood, it allows the boat to move faster. Whether you're a sailor or passenger, it's nice to know you can count on its support. Production begins with a strip of carbon fibre, which is wrapped around a long mast form that will serve as a mould. The material is trimmed and the paper backing is peeled away. Between 20 and 100 layers will be wound around the mould, depending on the size of the mast. Some layers are applied in a crisscross manner to give the mast more structural integrity and to hold its shape. The overlap is cut away so that the edges meet perfectly. The material is slightly creased and bulky at this point, so it's wrapped with plastic tape to compress it, which is then removed. This temporary taping is done after each layer, and the tape is left on after the final layer before a breather cloth is taped around it. Then, a plastic vacuum bag is pulled over the entire mast. The ends are sealed with tape. The vacuum connector and hose are attached. The vacuum sucks air from between the carbon layers and compresses them further. Next, it all heads into an autoclave to be baked under pressure. This will squeeze more air from the layers. At the same time, the heat will activate glue impregnated into the material, permanently fusing the layers. This fitting is made in a similar fashion. It's called a gooseneck plate and will connect a boom or spinnaker pole to the mast. Back to the mast. The large aluminium mould is pulled out of the mast tube. The surface is roughened using a disc sander, so paint will stick. 2 holes are drilled. And using a jigsaw with a special blade, the holes are connected, creating one wide slot. The gooseneck plate is trimmed to fit snugly on the mast. Next, a plastic pipe with a string on the end is manoeuvred. The string is threaded through the mast tube. Then it's hooked and pulled out of the slot made earlier. It's a messenger line, and it will be used to install the rope halyard that will raise the sail. Messenger strings are also used to install electrical wiring, connecting such things as radar, horns and lights. They're all funneled through the inside of the mast. The mast has now been painted, and the upper end of the pulley system for the halyard is installed. A pin that holds the halyard pulley is slid in, and a guard to keep the rope from fraying is bolted on. Next, a wind indicator is screwed on. A signal light is locked on to the top of the mast. It will indicate the boat's direction to passing vessels. A piece called the toggle is attached. It's a connector piece between the gooseneck plate and the boom. This carbon fibre mast is now seaworthy and should make the trip a real breeze. Plain sailing, really. The fortune cookie is a munchie with a message, and the message is usually as sweet as the sugary shell. But there is one surprising thing about the fortune cookie. It wasn't invented in China, but in California in the early part of the 20th century, and people in China have never really developed a taste for it. To make a batch of fortune cookies, the process begins with a bag of sugar. It's emptied into a large steel mixer. Fortune cookies are about 20% sugar. Some food colouring is added, just enough to turn the cookies that distinctive golden shade. Then some melted vegetable shortening. They pour in some starch to act as a thickener. Pipes spray water into the mix, and then the pastry flour is added. This soft wheat flour will give the cookies their texture. More water is added because too little of it would make for a crumbly batch. Then it's time to mix it all up. After a few minutes, the consistency is checked. Once that's blended in, the cookie mix ebbs from the bowl as a hose pumps it out from the bottom. Next, ejector nozzles squirt the batter onto hot moving trays, making biscuit-sized pieces of the mixture. You could call this the Wheel of Fortune cookies. Hot moulding plates revolve. Each one descends and presses onto 4 fortune cookie portions, flattening and shaping them. They travel through an oven that's over 9 meters in length and bake for about a minute. They come out of the oven piping hot and are given no time to cool down because they need to stay soft so they can be easily manipulated in the next step. Steel prongs push little paper fortunes into each cookie as they fold it into that distinctive butterfly shape. There are 5,000 different fortunes in the mix at this factory. So you could say a lot of thought has gone into this process. This plant makes 4 million fortune cookies every day, enough to make a small fortune. The folding moulds open as the track descends. The fortune cookies, now cooled and crispy, drop to a conveyor below. It takes each fortune cookie through a wrapping mechanism which envelops it in plastic. Then, a hot blade cuts and seals the package in one fell swoop. The packaged fortune cookies transfer to another conveyor, which transports them to an inspection station where many production lines converge. The cookies and their packages are checked for breakages. Any rejects are tossed away. After all, a broken fortune cookie could be bad luck. A box moves into position and hundreds of cookies fall into it. 350 cookies to be precise. They're portioned out by a scale overhead. Then, a plastic ram gently presses the cookies into the box to reduce the bulk. A conveyor belt moves the box full of cookies under a metal bar, which pushes the flaps down to close it. And now the time has come to crack open the cookie in the proverbial ritual. It looks like this could be our lucky break. Coming up on How It's Made, IMAX projectors. We give you the big picture. And roller chains. Can't think of a link for this one. See you after the break. The movie projector was invented over a century ago, and the concept is the same today. Film revolves in front of a light which projects an image onto a screen. But the latest technological advancements make the projector a real showpiece. Its film is 10 times larger than normal, and the projector magnifies it 400 times, as it moves it in a sideways rolling loop, rather than the traditional vertical feed. And instead of the usual sprockets, registration pins retract as the film loads, and then reach out to steady it as it rolls. A vacuum sucks the film to the aperture lens. This is how they keep the gigantic image perfectly steady. To make an IMAX projector, 2 prisms are bolted together and mounted on a part called the lower illumination module. The prisms and the mirror will reflect the projector's light to a similar part called the upper illumination module, which will relay the light to the lens. It's a fly's eye lens, a collection of mini lenses on one glass. Each will focus to a single point, ensuring an even distribution of light. A technician screws 2 fly's eye lenses together and then places them in a fixture to align the 2 halves. He switches on a light and places an alignment guide over the lenses. There are red and green filters on this guide, and he brings them into focus. He adjusts them until the red and green lines merge. It means the 2 lenses are now aligned. Next, the upper illumination model is installed in the projector frame. And then they flip it. The protective cap is removed from the back. Then it's attached to the lower illumination module, which we saw assembled earlier. Here, the rotor support and motor are bolted together. This large wheel is the rotor, it's the heart of the projector. It drives the film forward in that distinctive, wave-like action. This piece, called a stator, will act as a guide for the film. The aperture block is fitted to the front of the frame. It's lowered onto the base using a crane. Spacer bars are screwed in. And the second projector assembly is installed. These two assemblies will enable the system to run three-dimensional movies. Now it's time to position the main lens at the front of the projector. The lens caps are removed and it's ready to roll. The film wave happens 24 times a second. We've slowed down this footage so you can see it all happen. The film of a test chart ripples in front of the aperture, and then vacuums pull it down for a 24th of a second. This eliminates any shakiness in the projected image. Now we're showing it in real time. So you get the picture. There is also nothing ordinary about the lamps the IMAX projector uses. They're very powerful, but they use the light very efficiently. And now, it's time to enjoy the show. Roller chains really keep things moving, and without them, a lot of important equipment would be powerless. Chains transfer energy in industrial and agricultural machinery, and without one, your push bike would be going nowhere fast. To make a roller chain, a punch press pulls steel from a giant spool. Using 500 tons of force, it cuts shapes out of the steel. These shapes are the link plates that will join all the parts of the roller chain. The plates travel on a series of conveyors. An arm positions them as they head towards the next punch press that makes 2 holes in each link plate. Then they're poured onto a tray and spread evenly across it. A vibratory mechanism shuffles them into a blazing furnace. This heat treatment toughens the steel. Then they cool down slowly in a tank of oil. After that, they go for a tumble in the washer to get rid of the oily residue. Meanwhile, another machine uncoils some steel to make bushings or sleeves for the chain pins. The blade slices the material to the correct length. Then mechanical arms fold the steel around a mandrel. Here's the action in slow motion. In real time, it all happens faster than you can blink an eye. The bushings fall into a bin. And now they're ready to be heat treated. A rail car takes the bushings into a furnace. This may look destructive, but the bushings will come out stronger. Now it's time to make the pin that will hold everything together. This machine shoves a steel rod into a jig and a saw cuts it to size, which varies depending on the chain it will be used for. A mechanical arm then picks up the pin and transports it to rotating heads, which machine down the ends. The pins then travel across a grinding wheel, which reduces them to a specific diameter. Next, they go through a wash cycle. A special mix of lubricant and solvents rinses away the residue from the grinding. These are the pins before and after grinding. Now it's time to put the pieces together. This is a breakdown of what happens at a blurring pace on the assembly line. The link plates and bushings go into an assembly device. A ram presses them together. They're removed and 2 more link plates are placed in the device. Rollers are positioned on top of them, and the bushings and link plate assembly are slid into place. It's all press-fitted together. And now they have links for the roller chain. The next step is to fit the roller links together. They're clamped into a fixture, and pins are slid in. A hydraulic ram presses the pins to the base of the assembly. Then the pins are connected with another link plate and pressed in place. This is repeated as the roller chain is lengthened. It can also be widened to enable it to handle more horsepower. To do this, single strands of roller chain are stacked. Longer pins are used to hold all the layers together. Again, a fixture holds it in place while the ram does its work. This produces heavy-duty roller chain. The one shown here can handle 400 horsepower. Finally, the roller chain is lowered into a vat of hot grease to lubricate the joints. And that's the chain of events that leads to the roller chain. So, whether you want some wind in your sails, or a sneaky look at your future, or a wanting to see the bigger picture, now you know how it's made. Today on How It's Made. Firefighter helmets, helping the fireman to keep a cool head. Nautical compasses, we take you on a voyage of discovery. Packaging tubes, we managed to squeeze into this factory. And handsaws, we couldn't cut anything from this story. But first, organised firefighting dates back at least as far as ancient Egypt, but the first municipal fire brigade was established in Edinburgh in 1824. Firefighters' helmets have been made from many materials, ranging from brass to Kevlar. This North American leather helmet is strictly for the hot-headed. Leather is surprisingly flame-resistant. When reinforced, it also makes for an extremely hard hat, offering protection from heat, dangerous liquids, and sudden impact. On this newer model, the accessories shield the eyes and ears too. Production begins with 4 die-cut leather sections. They're sewn together to make the skull of the helmet. This piece will become the brim of the helmet. To give the skull structure, each section is folded and sewn. Then the crease is flattened with a special hammer. A template is used to score a sewing line in the leather. Then the sections are joined together using a powerful sewing machine. The 2 halves are joined together and reinforced with double stitching. The resulting 8 ridges give the skull stiffness and strength. The leather is stretched over a plastic mould, and any excess leather is trimmed from the ridges. Then 4 vice grips are clamped to the rim. These attach to a hydraulic jack that stretches the skull overnight. After glue is applied to the ridges, they are run through compression rollers to create a tight bond. The brim piece is wetted several times to make it more pliable. Then it's stamped with a design used by this company since 1846. A wire is inserted that will give the brim some structural support, and then a temporary plastic cover and lid are put in place to ensure an even spread of pressure across the brim. The edges of the leather are stuffed inside before the press applies 10 tons of force to imprint the design. Next, the skull is sewn to the brim. The excess leather at the base of the skull is removed, and the centre of the brim is cut out. Then, the plastic mould is removed. In order to seal the leather, the hats are dipped in a vat of hot rosin, a type of tree sap. After 55 minutes, they're removed and left to dry at room temperature for 8 weeks. This slow drying process makes the leather as hard as wood. Drying it mechanically would make it brittle. To make the inside, a plastic cap is inserted to reinforce the structure. The fit is intentionally tight, so a mallet is used to tap it into place. Inside this, another plastic cap with nylon straps is added. This will help to resist the impact of falling objects. An acetylene torch is used to burn off any loose threads and soften the leather so that the brim can be bent and the ridges can be straightened later on. Turning up the sides is basically an aesthetic gesture. The longer edges at the back will direct water away from the neck. After a synthetic fire-retardant liner is added, the outer surface is sanded to prepare it for painting. First, a fire-retardant chemical primer is added. Then a semi-gloss latex paint in firefighter's black. Or if you prefer, a clear varnish to show off the natural leather. A front piece with the firefighter's signature brass eagle is added on top. And then some fluorescent stickers for extra visibility. And you've got the right headgear for a hero's job. For almost 2,000 years, the compass has been helping people find their way. It was first developed in China, before eventually East met West, and European sailors began using it to chart their course. They soon realised they'd be lost without it. This device is used to magnify a special metal alloy. A technician slips a retainer ring onto a jig and positions the magnet on top of it, before placing an aluminium skirt over the magnet. This will support the compass dial, which goes on next. A pivot needle is inserted into the centre, which will allow the dial to rotate. Then all the pieces are press-fitted together. Chemical cleaner is sprayed into the pivot cavity. It has to be spotless because any dirt would impede its function. A small jewel post containing a tiny sapphire is also cleaned. Then the jewel post is fixed in the dial. The post will support the dial while allowing the pivot needle to move easily, as it's pulled by magnetic forces. The dial is placed on a machine that mimics the Earth's pull. A weighted paint is brushed on the back of the dial to counteract the pull. This balances the compass dial, preventing false readings due to differences in the planet's magnetic force. These are lubber lines, small direction markers. They're inserted into holes in a jig and lined up with holes in an aluminium gimbal pan. The lubber lines are pressed into the pan. Now, 2 pins that allow the ring to flip around the gimbal pan are inserted into the gimbal ring. Then the compass dial is attached to the gimbal assembly. The technician spray paints the metal compass bowl black and pops a rubber diaphragm onto it. A bronze ring will hold it in place. This flexible rubber liner will contain the compass fluid and allow it to expand and contract. The dial and gimbal setup are snapped onto the bowl. To level it out, a small tab is bent over. An acrylic dome is positioned on top. Using another jig, a rubber ring is put over the dome to seal it, followed by a metal collar. With a power screwdriver, these pieces are anchored to the rest of the compass. Then, fluid is pumped into the bowl, filling the dome. The fluid magnifies the numbers. Next, 2 metal rods are magnetically charged and installed in the compass base. These will compensate for magnetic fields on the boat. A metal housing unit is mounted on the base. Then shock absorbers are attached to cushion the compass against vibrations. The compass is installed in the housing. Tapping the dome tests the shocks. A decorative aluminium cover fits around the dome. Then a light is installed to allow the navigator to see at night. Iron spheres are attached, another tactic to counter magnetic interference. Our journey through the plant is now over, and the compass is ready to set sail. Coming up on how it's made. Packaging tubes. We'll see just what this factory contains. And hand saws. This product is a cut above the rest. See you after the break. The tube's design lets us squeeze out the product and yet still read the fine print on the twisted package. Artists first used flexible metal containers for their paints back in 1841. Nowadays, we use them for products like glue, skin cream and toothpaste. Remember, don't leave the top off. These packaging tubes are made of aluminium because it's affordable, lightweight and malleable. This company makes each tube from an aluminium slug. A batch of slugs are dumped into a container and a lubricating powder called zinc stearate is added. The container spins, causing the powder to coat the slugs evenly and prepare the metal for stretching later on. The slugs then spin around in another container, which aligns them horizontally so they'll fit through a channel at the bottom. The channel feeds the slugs into a forming press. In a process called impact extrusion, each slug moves onto a die, which gives it the exterior shape of a tube, including the neck. At the same time, a mandrel forms the interior. This process hardens the metal, something that will be corrected later on. The machine applies 200 tons of pressure to as many as 150 slugs per minute. They can be as narrow as 1 centimetre and as long as 22 centimetres. This machine uses compressed air to align the tubes for the next step. A trimming machine cuts threads into the necks by passing each one between 2 synchronized rollers. Stationary blades trim the top of the neck, making the surface smooth and safe to handle. The neck on most models remains sealed until the consumer pierces it. Another company eventually seals the tube by rolling up the other end, after the product has been inserted. After they've been heated in order to soften the metal, the tubes move through another machine. Nozzles spray the inside with 2 coats of epoxy lacquer. This creates a protective barrier between the aluminium and the eventual contents. Rollers apply a coat of polyester enamel paint, which is flexible when dry and resistant to most solvents and sun damage. Grippers place the tubes on long pins, which move them through an oven for 7 minutes, so the paint can dry. From there, it's off to the printing machine. Each tube makes 1 complete rotation against a printing plate. The plate applies a coloured image and information that describes the tube's contents. Then, they go back into the oven to dry the ink. The printing's legible even when twisted because the polyester ink remains flexible. Another machine applies a kilo of torque to screw on the plastic caps. Most of the caps have pointy tops, used to pierce the sealed neck of the tube. They use flat caps to close off tubes with open necks. On the next machine, nozzles spray on a strip of latex sealant inside the open end of the tube. The latex is like a gasket. After the product is inserted, it seals the tube when the end is folded over. After a machine packs boxes with an average of 300 tubes each, the inside of every tube is inspected. A bright spotlight reveals any chips in the paint that makes the packaging deficient. About 1 in every 500 tubes is flawed. A sheet of sticky paper over the open ends of the tubes keeps them from twisting during shipping. And a label on the box provides tracking information and a way to show off if someone has tampered with it en route. Then these tubes will leave the factory. And so will we, because that's all the information we could squeeze out of them. The handsaw continues to make the cut. You'll find it at every building site, always at the ready. Power tools are higher tech, but the handsaw has a basic appeal. It doesn't need an extension cord and almost never breaks down. It's a trusty tool with the teeth for the job. Handsaws come in many sizes. To make them, a machine uncoils steel and draws it into a mechanized punch. The punch works at a blurring speed to cut teeth into the steel, 140 notches every minute. Here it is in slow motion. It makes 2 cuts for each saw tooth. A reel takes up the newly serrated steel and then feeds it back to cut teeth on the other side. Next, a finger-like device unrolls the steel and pushes it towards automated jaws. The jaws bend the teeth, alternating the direction of each one. Here's a look in slow motion. This is called setting the teeth. A die punch cuts the steel coil into pieces called double blanks. Double because 2 saw blades will be made from each one. The die also makes holes in one end of the double blank for attaching handles. The double blanks are fed into a shearing machine. A blade descends and cuts it in half along the diagonal, making 2 saw blades. The blades are pressed against the sanding belt to smooth out the edges. This is called deburring. Here, they're making a higher-end saw blade. A piece of steel is flushed with coolant as a machine grinds it to make teeth. This method is more time-consuming, but results in a superior tool. Again, the teeth are set. But this time mechanical jaws do the job a blade at a time, rather than working on one long coil of steel. The teeth will need to be strengthened in order to perform. So rollers move the blades to an electrical coil. Within milliseconds, the temperature of the blade shoots up to almost 900 degrees Celsius. This tempers the steel. The blades drop off the conveyor into a bin. Here's a look at the blade before heat treating. And this is after. The black burn line is a sign this saw can take the pressure. A conveyor wheel dunks them in a pool of clear protectant. This will keep them looking shiny. One is placed on a table. It rises and a squeegee silk screens the company's name onto it. At this point, the ink is still wet. 30 seconds in an infrared oven is enough time to bake on the brand name. Cardboard sleeves are slid over the blades. And now it's time to get a grip. 2 plastic handle parts are fitted together and placed on a carousel. An ultrasonic sealer moves in. It emits a high-frequency sound, and the vibrations melt the 2 plastic pieces together, forming a handle. The handle is fitted onto a blade before a machine rivets it in place. Some saws have wooden handles. Because riveting could split the wood, they are bolted on with screws. And there you have it. Tools that are cut out for the job. So, whether you're looking to keep a cool head, or you're all lost at sea and heading in the wrong direction, or perhaps you just fancy a little squeeze, now you know how it's made. Today on How It's Made. Halogen bulbs. Making them is a truly brilliant process. Cellulose insulation. We thought it was time to fit this one in. Aluminium ladders. Finally, this programme is on the way up. And bamboo fly rods. We cover all the angles to look at their construction. But first, halogen headlights are a shining example of progress. The halogen bulb throws cool white light that mimics daylight illuminating the road ahead. And because they're energy efficient, they don't burn out too often. A real plus when you're trying to keep your eye on the road. To make a halogen headlight, mechanical jaws load 3 lead wires into a machine. A gripper moves in and bends the wires at the bottom. Meanwhile, a conveyor system feeds small glass rods to a burner. The softened glass is now pressed onto either side of the lead wires, encasing them. Next, a welding head fuses tungsten coils to the lead wire assembly. The coil is the filament, the part of the bulb that emits light. At another station, a mechanical arm loads a glass tube into a machine head. A burner aims a flame at the centre to soften it up. Then, mechanical heads pull the glass at both ends as the burner continues to fire heat at the middle. This creates a neck in the tube. Now, mechanical arms position the coil and lead wire assembly under the newly shaped glass tubes. Grippers lower the glass tube over the wires so they sit under the neck. Burners move in and encircle the glass at the bottom, softening it. Then a press seals the glass around the lead wires, which protrude from the bottom. Next, a test. An electrode sparks the lead wires. When the capsule illuminates, it means there's ambient air inside that would interfere with the bulb's function. Vacuums at the top of the bulb suck out all the air and contaminants. Then nozzles spray liquid nitrogen onto the bulb. This freezes it inside and out, creating a pressure difference. That change in pressure pulls halogen gas into the bulb from a chamber above. Allowing no time for the gas to escape, burners heat seal the bulb at the neck. The bulbs then cool as they move on a transfer chain. Grippers now load the bulbs into another machine. A pusher moves up and snaps a steel retainer around the bottom of each bulb. Meanwhile, another machine builds the base for the bulb. It pushes electrical contacts into the plastic receptacle. This is the view from the bottom. These prongs will eventually connect the headlight to the vehicle. Next, jaws turn the bases over. They load them onto a tray on tracks. The tray delivers the plastic bases to a mechanical arm that installs metal retainers on each one. The bases slide forward, and the machine inserts the glass bulbs into them. But it's a loose fit. This machine aligns each bulb to its base. Jaws tilt and slide it into place. Then a laser welds it together. The alignment is critical. Coils for the low beam and high beam mechanisms must be precisely positioned. Next, a series of claws pick up the bulbs and dip them in an opaque coating called black top, because it only covers the tops of the bulbs. This will direct light out of the sides of the bulbs. Now it's time to take these bulbs for a test drive. A bracket holds them down while probes underneath energize them to make sure they work. A plunger places a gasket around the base. This will seal the headlight capsule to the car. And now they're ready to shed some light on the situation. One type of insulation material is cellulose fibre, made from recycled paper. It's derived from a natural source, wood fibre, so it's non-polluting. It contains no asbestos, no fiberglass, and no formaldehyde. Insulation keeps your home warm in the winter and cool in the summer. Like other insulation materials, cellulose fibre has to meet strict government safety standards. One fire safety test assesses smoulder resistance. A sample from the production line is weighed, and then a lit cigarette is inserted into it. Once the cigarette burns out, after about an hour, the sample is weighed again. The weight loss must be less than 15%. Making cellulose insulation begins with recycled paper, delivered in bulk. It's loaded by hand onto a conveyor belt, and from that point on, the entire process is automated. The paper goes into a machine called the primary mixer. It separates the bunched up pieces, preparing them for shredding. The machine's powerful magnet removes staples, paper clips, and other pieces of metal. From there, the paper goes into a shredder, which rips it into pieces about 5 centimeters long. The shredded paper is mixed with boric acid, a natural compound that acts as a fire retardant. It also makes the insulation pest resistant, and it helps fend off mold, wood decay, and corrosion. Now a machine called a fiberizer shreds the paper into tiny pieces about 4 millimeters long, and it mixes them with more boric acid. From the time the recycled paper arrives by truck to the time it comes off the line as cellulose fibre insulation, only about 5 minutes have passed. The insulation doesn't leave the factory before undergoing thorough safety testing. This test assesses what's called open flammability. The insulation is heated to 50 degrees Celsius to stimulate the temperature of a roof in the hot sun. Then it's ignited. The flame travels but then dies out, thanks to the boric acid. If that happens within a certain distance, the insulation is safe. Outside research firms also test the product for safety to verify the results of the company's tests. The automated packaging equipment blows 11.3 kilograms of insulation into a bag, whilst at the same time compressing the fibre into a block. Some types of thermal insulation come as thick rectangular blankets known as bats. These will be installed by hand, fitting snugly between the wall studs. Cellulose fibre doesn't come in bats. It's known as loose fill insulation. A professional installer has to inject it in between the walls by spraying it in under pressure. It fills all the spaces without any gaps, something that's hard to do with pre-shaped bats. Insulating performance is referred to as R value. The higher the R value, the more effective the insulation. Cellulose fibre insulation has a higher R value than loose-fill mineral fibre insulation, and a similar R value to loose-fill fiberglass. Cellulose fibre is denser than other materials, so it resists air movement better, making it less likely to move out of place after installation. And it saves money on your heating bills. Coming up on How It's Made, aluminium ladders. We take a look at each step of production. And bamboo fly rods. Make sure you catch this one. See you after the break. The aluminium ladder is the height of convenience. Lightweight and sturdy, it makes any ascent easier. Wooden ladders used to be standard, but were extremely heavy, difficult to position, and would eventually rot. The use of aluminium took things to a whole new level. For a ladder to really stand up, the aluminium needs to be strengthened with these ingredients: silicon, magnesium, manganese, and copper. It all goes into a furnace. A crane transports a hopper full of aluminium over to the furnace. The hopper opens at the bottom to unload. A door is opened at the front of the furnace. The operator wears a face shield to protect him from the blistering 700 degrees Celsius heat. He adds the other ingredients, and the heat turns it all into a liquid mass. The liquid flows out of the furnace into troughs. It seeps through holes in the troughs to moulds in the ground. The liquid cools and hardens in the moulds. This makes log shapes that are almost 7 meters in length. A hydraulic lift extracts them from the moulds and slowly takes them to the next station. You wouldn't want to rush this job. Each log weighs 500 kilograms, and dropping one could do serious damage. A saw cuts them into pellets. The size depends on the type of ladder being made. A mechanical lift delivers a heated pellet to an extruder, and a ram pushes it into the opening. They move the die plate into position. The ram forces the hot pellet through holes in the die plate. This makes a rail shape 40 meters long. A puller drags the rail onto a table and leaves it to cool and harden. Then, a circular saw slices it into manageable 6-meter lengths. Each end of the rail is fed to jaw systems, which pull it to make it completely straight. The straightened rails now move on to the next station, where plastic feet are riveted onto the ends to keep the ladder from slipping. Safety information is stuck onto the rails, and the ladder is assembled, one step at a time. Each step is fitted in the rims of the ladder rails, then riveted in place. This will be the front of a light-duty stepladder. A diagonal brace is installed, and the ladder is turned over so that the steps can be riveted from the other side. A sturdy blue plastic top is fixed onto the front and back pieces, joining the two. The spreader is also installed and secured with rivets. And now, this stepladder is ready to provide a little elevation. For a lot of elevation, extension ladders are produced. Cylindrical rungs are used for greater strength. Each rung is fed to a machine which tapers the ends. Another machine presses aluminium ferrules onto each end. This allows the rungs to fit snugly into slots in the extension ladder side rails. Hydraulic arms reach from above and below to press fit the rungs into the side rails. Finally, workers rivet rubber pads onto the ends of the rails. This provides a firm footing for the ladder. These ladders are now complete, and if you're on your way up in the world, they'll come in handy. The bamboo fly rod is a classic. The split bamboo rod has been around since the early 19th century. These days, synthetic rods abound, but bamboo still holds a traditional appeal. People buy the idea, hook, line, and sinker. A bamboo rod is considered a work of art in fly fishing circles. To begin the process, a craftsman toasts a bamboo pole on an open flame. He holds it close to the fire, but not too close. One false move and he could scorch it. The goal is to turn the bamboo a golden brown. He pounds a wedge into the toasted bamboo and drives it down the length of the pole. The pole is pulled apart, splitting it in two. Then the craftsman continues to split the bamboo, making strips that are less than a centimetre wide. The bumps on the exterior of each bamboo strip are ground down using a belt sander. Next, it's over to the milling machine, which tapers the underside of the bamboo strip, beveling it to a 60-degree angle from end to end. This critical step will affect the rod's casting performance. Each strip has to be perfect. The rod maker inspects them for flaws and then fits 6 together in a hexagonal configuration. He wraps them with cotton twine to hold them together very loosely at one end. Then he dips the bamboo strips in a tank of thermo-setting glue. He feeds them to a twining machine, which binds the strips tightly together. It's a temporary wrap, a kind of clamp, to hold the pieces together while the glue dries. The pieces are now laminated into one, but the result is never perfectly straight, so the rod maker heats it over an open flame. The heat softens the bamboo, so the kinks can be smoothed out. Next, ferrules made from nickel silver are glued onto the laminated bamboo pieces. This tubing will be used to connect the tip and butt of the rod. The butt section now turns on a lathe, while a blade cuts into it. It's slimming down sections to accommodate the handle and reel seat. The walnut reel seat is slipped in place, and cork rings are slid onto the rod to make the handle. Each ring is glued. It takes 12 to 14 to make a handle for the typical bamboo rod. It will allow for a soft, non-slip grip. Once the glue hardens, the cork is shaped on a lathe. It's sanded to give an even finish. Next, some glue is heated over a flame. The hot glue is applied to the stainless steel tip and stuck on the narrow end of the rod. The model and serial number are applied onto the rod using black India ink. Now it's coated with varnish using a turkey baster. The rods are left to dry. It will take 3 coats of varnish to give them a nice gloss. Silk thread attaches the steel guides to the rod. These are the loops that the fishing line will go through. 3 coats of varnish are brushed onto the string. This solidifies the wrap and fuses it to the rod. A ring is slid onto the reel seat to provide a little separation from the cork grip. The butt and tip pieces of the bamboo rod are fitted together. It's taken 40 hours to make this bamboo fly rod. Now it's just a question of how long it will take you to catch that big one. So, whether you're looking to shed a little light on the situation, or hoping to maintain a steady temperature, or you're trying to climb to new heights, now you know how it's made. Today on How It's Made, drill bits will bring you the whole story. Photo booths exposing the secrets of their production. And stamps. We deliver a special 2-part report, so stick around. But first, a drill bit is used to create holes in a variety of materials. A countersink is a tapered hole drilled with a wide outer portion the same diameter as the intended screw head. A plug cutter removes a round piece of wood with which you plug the hole afterwards to hide the sunken screw. Kinda twisted logic. Countersinks and plug cutters start out as steel bars. To make a countersink, this computer-guided tooling machine uses a center drill to pierce a starting hole, then switches to its main drill, which bores right through. Next, it uses what's called a rough turning tool to shape the countersink's angled nose, then its body. The machine now switches to a milling cutter. This tool shapes the countersink's 4 blades. A cross-drilling tool bores a hole for the 2 screws that'll hold the countersink to the drill. A tap cuts threads into the hole. Next, a tool called a dovetail cutter sharpens the blades. Then finally, a cut-off blade removes the tool. The same machine makes plug cutters. Its center drill makes a starting hole, but this time, the main drill doesn't bore right through. It stops at the depth that the plug cutter is designed to cut. Just as before, the rough turning tool shapes the body, and the milling cutter sculpts the 4 blades. After the dovetail cutter sharpens the blades, a tool called a boring bar refines the hole in the center, making it the proper size. Another turning tool now forms the shank, the stem of the plug cutter that you insert into the power tool. Then the cut-off blade slices the tool off. Now for some manual touch-ups. First, they grind the plug cutter against an abrasive wheel to remove excess metal from the cut-off. Then the sides of each blade are ground to a particular shape that'll clear the wood chips. Here's how the plug cutter looks before and after grinding off the excess. And before and after side chipping. And now for making the drills to which the countersinks attach. It all starts with a tapered piece of steel, because this will become a taper point drill. Straight drills begin with a straight piece. A mechanical arm inserts this drill blank into a computer-guided grinder. The machine has two wheels made of boron nitride granules, a natural mineral that's tough and abrasive. The first wheel shapes the smooth blank into lengthwise spirals called flutes. A second wheel then grinds sharp cutting edges on the flutes and shapes the tip of the drill to a point. Back to the countersinks now. The steel is still relatively malleable, so a worker runs each one through a stamping machine that imprints the size of the tool and the company name. Countersinks and plug cutters must undergo a heat treating process to harden them. 20 minutes in a fiery oven with a secret recipe of chemicals. The intense heat, 955 degrees Celsius, transforms those chemicals into gases, which then permeate and harden the steel. After cooling in warm water and oil for about 15 minutes, workers submerge the tools in an industrial strength cleaning solution that removes all the grit. Then a bath in acid removes any soot. Finally, 20 minutes in a blackening solution, the ingredients of which are again a closely guarded company secret. This last step is purely cosmetic. Here's how the three drill bits work together. First, you use the plug cutter to make the plug. Then you pop out the plug with a screwdriver. Next, mounting the countersink, that black tool onto the taper point drill. You drill a hole for the new screw. Then you drive the screw into the hole, sinking it below the surface. Then you cap the hole with the plug. These tools come in an extensive range of sizes and grades for both amateur and professional woodworkers, and for industrial machines. Who said DIY was boring? Photo booths were first introduced in the 1920s in the United States. These small private cabins can take several snapshots or one large picture. Whether for passport or pleasure, they use the latest technology to take your portraits. Cheese! This model simulates a painting or drawing based on the photo it takes of you. To customize the pre-assembled cabin, a worker applies stickers to the outside. These advertise local businesses, or the booth's eventual location, such as a shopping centre or amusement park. Inside, there are 5 shelves for equipment. 2 layers of plexiglass are glued together. They will act as safety glass, protecting the equipment from vandals. They're fitted over an opening in the wall that divides the seating area from the camera and a TV monitor. A metal plate is installed in another opening. It will cover the coin acceptor and give the booth operator access to the money people pay to have their photo taken. The coin acceptor attaches to brackets on the back of the door. They'll program it to accept tokens or specific currencies. This 15-watt bulb provides some light for your photo. It goes in a panel that fits into the wall. Next, a motorized tripod to hold the camera. In this model, they use a digital camera with an 8mm lens. Up and down buttons on the control panel adjust the camera angle. A computerized voice from a speaker will prompt you to make selections. A fan attaches to the ceiling to vent the cabin and keep the equipment from overheating. And 2 40-watt fluorescent lights will provide most of the frontal lighting for the subject. Another 15-watt light behind a frosted panel provides some diffuse light. The booth's power panel has connections for up to 19 pieces of equipment. A camera is plugged in, then a TV monitor and an inkjet printer. Software will process the photos and the printer will print them on photo quality paper. A plexiglass window protects a 38cm monitor that's used for viewing and making selections. Two other monitors fit in windowed panels on the outside of the cabin. The monitors all connect to the computer and show the same images at the same time, including what stage of development your picture is at. They install a dispenser that sells optional cardboard frames for your portrait. Money from these sales falls through a slot into a metal coin box inside the cabin. The dispenser holds up to 100 cardboard frames, each large enough to hold one portrait measuring 20 by 28 centimeters. If the dispenser's out, a sign reading "out of frames" drops into the tray. For security, the two doors enclosing the equipment each have two key locks, one at the bottom and one at the top. The worker installs 4 signs on the cabin roof. They're plexiglass boxes with vinyl posters and fluorescent lights. The cabin's curtains lets you make goofy faces in private, but is short enough to let people know you are in there. Inside the cabin, the control panel helps you guide the camera. You press up or down to adjust the camera angle. Then you choose from one of 3 photos the camera has captured. The computer bases its portrait on this photo. You can tell it to make a caricature, a simulated work of art, or 4 small portraits in different artistic media. You can choose an oil painting, a pencil sketch, or a drawing in charcoal and pastel. So now you've got a masterpiece you can really identify with. Nice. Coming up on How It's Made, it's a How It's Made 2-part special as we take a frank look at stamp production. See you after the break. The world's first postage stamp, the penny black, was introduced in England in 1840. Until then, the person receiving a letter had to pay the postage. The penny black was black, cost 1 penny, and featured Queen Victoria's profile. Since then, stamps have come a long way. Today's postage stamps feature all types of illustrations. A graphic artist produces a design concept, working the computer cursor like a paintbrush on a canvas. Once approved, the design goes to the printing company. The printer produces one type of stamp using 2 different types of printing press, one of which requires an engraved printing plate. The company's master engraver draws his artistic interpretation of the concept, using photographs of real subjects for inspiration. Then he paints his drawings in watercolours. The shading is key because it indicates where the engraving will have depth. Once he's happy with the result, he scans the image into a computer and shrinks the digitized image to the actual stamp size. Then, he lays a sheet of clear acetate over the reduction. With a tool called a point, he etches the main elements into the sheet. This etching process is known as scribing. The scribed sheet is taped onto a piece of soft steel. The metal surface is coated with beeswax. Then the sheet is laid down again. and rubbed with a burnishing tool, transferring the scribed image to the wax coating. Now a microscope magnifies the image 7 times. The design is etched using a pointing-in tool. Then another tool called a lozenge engraver is sharpened. With that, the engraver deepens the etched lines of the design's focal point. This adds depth, which will make the deer appear almost 3-dimensional on the finished stamp. Once complete, the engraving will be copied onto a plastic master plate. The plastic is coated with silver so that it will conduct electricity, then submerged in a bath containing baskets of nickel. An electrical current is run in both the bath and the plate. This dissolves the nickel and draws it onto the plate in a thorough and even coat. The excess nickel along the perimeter is removed. Then the printing plate is extracted before being coated with chrome. Now it's ready to go into the intaglio printing press, a specialized machine used to print only selected elements on certain types of stamps. This machine, meanwhile, produces the templates for carving shablons, the rollers on the intaglio press that transfer ink to the printing plates. Here the machine traces a pattern for one of the stamp's intaglio elements, guiding a router on the other end to reproduce it, in half the size, in thick plastic. Meanwhile, at another machine, the shablons are made. Several ingredients are poured into a roller-forming machine. Exactly what they are is a closely guarded company secret. The mix heats to about 180 degrees Celsius. It thickens and hardens for about 90 minutes. Now, an automated routing machine with multiple heads goes to work. Following the plastic template, the heads carve away at the rubber, leaving behind a raised design in the shape of the elements the intaglio press will print. It's this raised area that transfers the ink to the printing plate. But these stamps are only halfway to their destination. Offset printing presses are widely available. So if an entire stamp was printed using that technology, counterfeiters would have it easy. Intaglio printing presses, on the other hand, are harder to come by, making fake stamps more difficult to reproduce, so you can be sure they come with a stamp of approval. The sheets first run through the offset press. It prints one colour at a time, inking a separate printing plate for each colour. The plate is wrapped around a cylinder. As it revolves, the plate transfers or offsets the ink image to the rubber cylinder rotating against it. As that cylinder turns, it transfers the image to the paper passing underneath. A postal service official inspects the press output. Using a magnifying glass, she scrutinises the colour and print quality, circling any problem areas for the press operator to investigate and correct. Now the offset printed sheets move onto the intaglio press. The intaglio shablon rollers spread ink over the printing plate the factory produced from the engraving. The ink fills the recessed lines of the image. The press runs the plate against the paper sheets transferring the image. Intaglio printing leaves ink slightly raised above the surface of the paper, giving the image a sense of depth. Once again, an inspector checks the results. It's up to the press operator to correct any errors, the cause of which may be as simple as a speck of dirt in the machine. Now that the printing has been done, The stamp sheets are loaded into a computer-guided perforating machine. Grippers pull the sheets forward, one section at a time. A die, with rows of steel pins, each just 1 millimeter in diameter, punches through the sheet, framing each stamp with tiny holes spaced precisely 1.5 millimeters apart. The machine knows where to punch these perforations by reading the line of fluorescent ink that runs along the borders of each stamp. This ink, called tagging, is visible only under ultraviolet light. The automated machines that process mail at the sorting plants are programmed to scan for tagging. All post without it will be rejected. After the perforated sheets have been stacked, they're trimmed down to the finished size. The trimming machine is called the guillotine, but unlike the head-chopping version, this one slices with a sideways shearing action that puts less wear on the blade. The machine holds the stack in place with 4,000 kilograms of pressure so that it doesn't budge under the weight of the blade. The blade weighs in at almost 32 kilos. Now it's time to group the sheets into manageable sized packs for post offices and other stamp retailers. This machine is called a vacuumatic counter because it uses suction to draw the sheets across a paddle wheel which counts them. This stack adds up to 503 sheets, so the worker removes 3 to make an even 500. The counter inserts a tab between every 50. Some stamps go through what's known as bursting, the process of manually separating pairs of stamps for different product lines, such as gift sets. Some burst stamps go onto first-day cover envelopes, one popular collector's item. An automated pad picks up the stamps and runs them against a wet roller that activates the adhesive on the back. After a worker positions an envelope against a guide bar, the pad places the stamps in a precise spot and applies even pressure over them, so that they'll lay flat and stick securely. Some stamps are still the old lick and stick type, printed on paper that's coated with a moisture-activated adhesive on the back side. However, the most commonly issued stamps, known as definitives, are printed on pressure-sensitive paper. That's the technical term for peel and stick. No water or saliva required. So, if you need the tools for doing that boring bit of DIY, or you're looking to expose yourself in public, or you simply want to communicate in the old-fashioned way, now you know how it's made. Today on How It's Made. Yacht wheels. This product needs to be shipshape. Braided rugs. We bring you the twisted tale. Car thermostats. Making sure you don't blow a gasket. And chisels. We chip away at the whole story. But first, the ship's wheel adjusts the angle of the rudder, changing the direction of the vessel. Helmsmen on older ships steered using a tiller, a long stick fixed directly to the rudder. The introduction of the wheel seems to have taken mariners in the right direction. This company makes yacht wheels as large as 1.5 meters in diameter. It uses two traditional shipbuilding woods, American holly and Burmese teak, species that are as beautiful as they are durable. Both types of wood are cut into long, thin strips that will become the wheel's rim. The strips are measured with digital calipers, then sanded down to a thickness of just 3.1 millimeters. Using a disc sander, the ends are angled into what are known as scarf joints. These angles will be fitted together to join the strips. After each strip has been coated with epoxy, it's attached with clamps to a round jig, which has been waxed beforehand to prevent sticking. The glue is waterproof because the wheels are often exposed to rough weather up on deck. Each 2-meter-long strip is gradually bent all the way around the jig. A spring-loaded clamp temporarily holds each end of the strip in place until the scarf joint is aligned with that of the next strip. It takes up to 8 hours of non-stop work to lay all the strips. The blonde holly and darker teak are alternated for a total of 7 layers. Then the rim is left to set overnight. To make each of the 5 spokes, strips of holly and teak are joined temporarily with double-sided tape. A computer-guided cutting machine then carves an opening through the middle and shapes the outer edge into a triangular shape. This reduces the spoke's weight and helps it fit to the rim later on. Next, the tape is removed and the wood strips are glued together, along with others made of carbon fibre, which strengthen the spokes while keeping it lightweight. A waxed jig is placed in the centre and clamped in place. The spoke is then left to set overnight. The next day, the dried glue is sanded away. Then a router is used to round the edges. Together, the 4 wooden and 3 carbon fibre layers are just 2.5 centimetres thick. A template is traced onto a stack of 14 curved strips of holly and teak, which has been pre-glued. Following these lines with a bandsaw creates a fairing, the component which will join each spoke to the rim. Now a hole is drilled in each fairing, and a dowel is inserted in order to position a reinforcing strip of carbon fibre at the top. To join the spokes to the rim, strong fiberglass dowels which were earlier glued to the rim are now inserted into the fairings and into holes in the spokes, also glued beforehand. The spokes are clamped to the rim through the openings. Then, an aluminium hub is positioned in the centre and tapped into place with a mallet. Now, with a jigsaw, a sliver is cut from the ends of the fairings so they will curve into the rim. A router rounds off the vertical edges of the wheel. The fairings are filed by hand to complete the smooth transition to the rim. These finishing touches alone can take up to 5 hours to complete. It takes another 5 hours to gradually round off the horizontal edge. To protect the wheel from the elements, especially sun damage, first a polyester primer is applied. Then this is sanded and 2 coats of waterproof varnish are added. Once aboard the yacht, 5 stainless steel bolts attach the wheel to a pedestal that connects to the rest of the steering mechanism. To change how fast the rudder moves, you simply turn a knob at the centre of the wheel. How's that for power steering? It's all plain sailing, really. For centuries, people have used braided strips of old clothing to make rugs. Today, high-speed machines create this classic look in a fraction of the time, but with synthetic as well as natural fabrics and yarns. So the rugs last even longer. This company's most popular rugs are oval or rectangular, some small enough for your stairs. The rugs begin as yarn. The yarn is bound onto bobbins that fit the factory's machines. The yarn ranges from pure wool to a blend of wool and polypropylene that makes the rug durable even outdoors. This machine braids yarn from 24 bobbins around a core of synthetic fabric. The result is a complicated weave called cable lock. Other rugs have just 3 braided segments in what's called a flat braid. Here, a powerful sewing machine is used to join flat braids with sturdy nylon thread. This makes one enormous piece the length of half a tennis court. The piece moves along a conveyor to an automated rotary saw that cuts it to size. The saw passes twice to ensure a clean cut through the 2.5 centimetre thickness. Another industrial sewing machine attaches binding tape to seal the edge. This prevents rectangular and square rugs from unravelling. Oval and round rugs don't need this because their braids aren't cut. This machine does what's called serging. It sews yarn over the binding tape to cover it, a purely aesthetic gesture. To make fabric rugs, several pieces of different fabric are joined along one edge. They're a cotton and polyester blend that's durable and easy to wash. After the fabric is wound onto a roll, a rotary saw cuts the roll to make strips that are 2.5 centimetres wide. The fabric strip then unwinds into a machine that folds it over a filler. This forms the core of the fabric tubes they call spaghetti. The machine wraps the fabric around the filler, then sews the edges to form a closed tube. Rollers guide the spaghetti out of the machine and onto bobbins. This machine weaves spaghetti from 3 bobbins into a flat braid. Fabric rugs are made only as flat braids because the material is too thick to weave into a cable lock. The braids settle into barrels for storage until they're woven into rugs. Sometimes, mats are assembled from a variety of braids for a different look. To make an oval or round rug, one continuous braid is coiled around itself. At the same time, each braid is sewn to the next. These rugs can have anywhere from 16 to 320 rows. The factory uses tables with holes that blow pressurized air to float rugs like this one as they grow heavier. The ovals range in size. They can be as small as a doormat and as large as a swimming pool. But when the rugs get really big, some extra help may be required. It takes about 2 hours to sew together one of these huge rugs. Lastly, a tag is stapled to the rug that reveals the size and style. Before the rug heads off to shipping. Perhaps more than any other floor covering, these rugs don't just lie there. The variety of styles and shapes mean they really tell a story at your feet. Coming up on How It's Made, car thermostats, how to keep your hot rod cool, and chisels, a truly cutting-edge tool. See you after the break. A car's thermostat sits between the engine and the radiator. Until the engine warms up, it blocks the flow of coolant to the radiator. When the engine reaches about 95 degrees Celsius, the thermostat opens, letting coolant flow through the radiator and into the engine to prevent overheating. Cool. The key component inside the thermostat is wax. When the engine heats up, the wax melts and the thermostat opens, triggering the cooling system. The wax melts quickly because it contains powdered copper, graphite and/or aluminium. As the wax transforms from solid to liquid, it expands. The pressure pushes a pin that opens the valve that enables the flow of coolant to the engine. After heating and mixing in the powders, workers pour the wax into slab-shaped molds. It takes about half an hour to cool and solidify. Then the slabs are extracted and ground up. The granulated wax is fed to a pill-making machine, the kind used by pharmaceutical manufacturers. It compresses the granules into cylindrical pellets. Meanwhile, a copper strip is fed into a machine called a high-speed transfer press. Its successive stations shape the copper cup that'll house the wax pellet. The first station stamps out a circle. The others progressively stretch and form the circle into a cup. The cups go into an automated assembly machine, which drops a pellet into each one. A pin then bores a hole down the center of each wax pellet. The machine inserts a rubber sleeve into the pellet hole and caps the sleeve with a brass cover. Then it crimps the cup over the cover, forming a seal that's leak resistant. Now the machine inserts the stainless steel pin that opens and closes the coolant flow valve. The pin goes right into the rubber sleeve in the center of the wax pellet. When the thermostat is operating, the melting wax expands within the cup, squeezing the rubber sleeve that forces the pin upward, opening the coolant valve. Now the parts are heated to the temperature at which the engine cooling system should kick in. A calibration machine squeezes the cup until the pin rises enough to open the coolant valve. The components now enter a machine which connects that valve. The valve is made up of two stainless steel pieces. The machine loads one on top of the other, over the thin end of the cup. Then pushes the valve over the end of the cup, attaching it to the wide end. On the left is before the valve installation, and here's after. Meanwhile, a press forms the top part of the thermostat, called the flange. It's made of stainless steel, coated with a lubricant. As with the cup, a series of dies progressively forms the flange. Now for the final assembly. First, the thermostat's stainless steel frame. Next, a stainless steel spring. Its job is to close the valve when the engine cools. Now the assembled components go inside the spring. The flange goes on top. A tool called an orbital riveter flattens a tab on either side of the flange. This holds the frame onto the flange. The assembly machine now crimps two little tabs against the pin, keeping it from falling out of the rubber sleeve. And with that, the thermostat is finished. This demonstration shows how as the engine heats up, the melting wax pushes the pin upward. And when the engine cools, the opposite happens. So even if you boil over in heavy traffic, your engine won't. A chisel is a metal tool with a sharp end for shaping stone, metal or wood. You use your hand, a hammer or a mallet to drive it in and cut. Although chisels date back to ancient Asia, today's factories use heat-treated steel and high-tech machines to make them stay sharper, longer. A wood chisel needs to be very sharp, especially for intricate carving. Making chisels starts when they insert a 5-metre-long bar of high-carbon steel in a mechanical press. The carbon lets them heat-treat the steel to give it a long-lasting edge. But first, the press cuts the bar into 22-centimetre-long rods. The rods then go through an induction heater. In just 6 seconds, a magnetic field heats them to about 1,300 degrees Celsius, a temperature at which the steel can be forged. Each rod is set into a die in a forging press. The die slams down, applying 700 tons of pressure. This produces what's called a forging, a rough shaping. The die can produce as many as 60,000 forgings before it wears out. Each goes into what's called a trimming press. Here, a die cuts out the precise shape of the chisel, with the blade on one end and the tang on the other. The tang later fits into a plastic or wooden handle. The factory sends the excess metal out for recycling. After the chisels cool off for several hours, workers run them through another induction heating machine, this one with 2 coils. The first heats them to 760 degrees Celsius. Then warm water cools them down. This rapid reduction in temperature is called quenching. The process gives the chisels their strength and durability. The next coil heats them to about 370 degrees Celsius. This step is called tempering. It relieves the stresses that the quenching phase created inside the metal. Spring-loaded clamps now release the chisels from the machine, and they drop into a container to cool overnight. The next day, workers can start to polish and sharpen the chisels. That removes the metal discoloration the heat treating caused. To polish the barrels, the round area joining the blade and the tang, workers load the chisels into devices called chucks. These clamp the chisel securely by the blade as the barrels spin against the rough grit sanding wheel. After about 7 seconds of sanding, the blades are ready for polishing. A powerful magnet locks them in place on a round table. It rotates, running the blades against an abrasive grinding wheel. As water cools the metal, it also applies a rust-proofing chemical to the steel. This polishing cycle takes about 20 seconds. The highly polished finish is a key selling point. Now to sharpen the blades. The chisels are loaded into another machine. It moves the chisels back and forth against another grinding wheel. After about 5 minutes of this, the blades are razor sharp. Only the last centimetre of the chisel, sloping at a 22-degree angle, is the cutting edge. This factory uses pre-formed plastic handles for its chisels. A hot metal die with raised lettering presses and melts a coloured plastic ribbon into each handle. This imprints the company logo, the model size, and a reminder to wear safety goggles. The next machine puts a steel cap on top and forces the tang inside the hole. The cap reinforces the handle against hammer blows. The tang stays put because it's fractionally bigger than the hole it goes into. The finished tools come off the line. Now you can have those chiseled features you always wanted. So, whether it's your turn at the wheel, or you've been told to wipe your feet, or you're simply trying to keep you cool on your commute to work, now you know how it's made.